Hey guys, how you doing? I won't be hearing noise. It shouldn't be anything crazy though. Here it comes. Alright. Are you able to hear the crickets? Yeah, okay, you are. Okay, great. Yeah, I moved the microphone so it's central now in here, and you'll also notice that there is a second camera that you can see, and that second camera is down in the lower left, obviously, and that's actually showing you inside the dome. See, here I am. Hello. Telescope's behind me, and it's meant so that I can actually keep track of what you see. Thanks, Dave. And I will be able to see the chat now. I made a few changes, as you can see on the screen. So we're working at trying to get this going with a little bit more panache, as they say. So that said, let's begin. And I'll start with a sip of Snapple iced tea. Snapple Raspberry is a very, very good tea. I love it very much. You can't really see it, but that's okay. And no, they're not a sponsor, not yet, but who knows. So, hopefully, some of the mystery of what's going on here can be cleared up by actually seeing the telescope here and seeing what we're doing. So, the telescope is here. This is the back end of the camera over here, which I don't think you can actually see too well. It's kind of just it's right there. You can see the light of the back of the camera. This is the cabling, which goes to the special capture system on the computer. And everything is configured. And I am actually controlling the whole telescope using an iPad with Wi-Fi. So we actually have the ability to go to different objects this way. And I know it's loud, but you'll hear me saying moving, as some of you are familiar with me having done. And when I say moving, that's the key item for getting us to the next place without you blowing out your eardrums, because I know it can be pretty loud. So that said, I'm going to just get this up and running. Let me just move. Alright, slow this down a little. Just slowing down the speed here a little. There we go. Okay, this is our first target for tonight. It's one we've seen before, but we don't have a moon, and it's going to be a little prettier now when we look at it. I'll bet you know what it is by now. This is actually Albireo, which is it's actually Gamma Cygni. It's actually a very beautiful orange and blue star, and it's a double star. So those two stars are orbiting around each other, which I think is a fascinating thing. They actually do have a solid orbit around each other, and that's kind of cool. Hang on, as local rednecks go by. There you go. That was the Harley crew going by outside. So now the moon's not going to rise for about just over an hour, so I think I want to take advantage of that and find some places that we can go. Now, when we look up at the night sky, you have to see what I see. I mean, I see so many stars, and I see beautiful beginnings of the Milky Way, the summer Milky Way, and it's actually very pretty. And you know, it's almost a shame to actually be in the dome, but the dome protects me from bears and other things that are in the neighborhood. So we want to be a little bit careful. So the next thing that we're going to go look at, I think, is something that I wanted to look at before. And this might be an object to look at. Hang on. I'm digging. Where is that? Oh, I know what I wanted to show you. Oh, come on. Right. Hang on, I had a connection failure here. That usually means that my Wi-Fi went away for this. Okay, let's see here. It's kind of interesting because I had a perfect Wi-Fi connection, and then as soon as I started the stream, the Wi-Fi connection to the iPad went away, which shouldn't happen. So I don't know why that happened. I'm going to continue to try to get it. One second here. Turn it back on. Reacquire. And by the way, just so you know, I'm investigating satellite tracking software that I can use with the scope, so that when a satellite enters the field of view or comes in, we can actually track it with the telescope and watch it going against the background stars. I think that's going to be a really cool thing if we can get that to work. So that's the next step. But among the other steps is the automation gear. I have to get this entire observatory automated so that we can run it entirely remotely. And that's the iPad is part of that. So I'm trying to do that. Okay. I had to restart the Wi-Fi for some reason. Alright. Alright, so I'm going to move up to an object that's just above Albireo. That double star was Albireo that we were looking at. And let's see what I got. Yeah, I love the crickets too. The crickets are cool. And now what I'm going to do is I'm going to take a photo. I don't see it in there yet, but you know, we'll see what happens. I'm going to actually increase the ISO to 10,000. We're going to take a 4-second photo at 10,000. Alright, so it's taking a picture now. Let's see what we get. There it is. I'll bring it back. Okay, just below center there, you actually see our target. This is a, This is a globular cluster And this globular cluster, okay, I keep hitting the wrong thing. This globular cluster is actually a very fascinating target because it's actually part of our galactic halo. Hang on, why am I getting... one second. I don't believe it. I did a boo-boo. I will leave it on that picture, and I actually have to go in to my office and grab the memory card. I forgot the memory card in here, so it's not giving us the ability to view the cluster with any kind of detail, and I can't save it. So now that I've got you in here and I'm streaming, give me about 30 seconds, I'll be right back, okay? You can listen to the crickets, I'll be right back. Okay, told you I'd be right back. So I apologize for that. And now I'll put the card in and take another picture, and then we'll be able to properly do what we wanted to do. So, 1 second. And we're going to take a 6-second exposure at an ASA of 10,000 of this globular cluster. There we go. Now, part of the reason that I do this is so that I can actually focus and get critical focus. So that's something I'm going to do now that I have this. So if you just give me 1 second. Critical focus is here. Okay, I'll let that star image calm down, and then I'm going to focus on it now. That's out of focus, as you can see. Remember our trick for seeing the colors of the stars. You take a star out of focus. So you can see that this one is kind of a bluish white. Okay, see, that's better focus. So now we come out and we'll take another photo, 6 seconds at ASA 10,000, sensitivity of 10,000. And now, when we look at this, it's going to look a little better. So these mysterious objects, these are out there in our Milky Way. Which is our galaxy, and you know, this particular one is actually one that's, again, these are all very far away. This one's 31,000 light years from here, and it's made of old stars. Now, these stars are called the early stars are actually metal low metal stars. Now, metal content in the periodic table of elements is such that anything other than hydrogen and helium and some of the gases are called metals. Even though they're not really metals, that's just terminology. And these stars that you're seeing in this cluster are what are called metal poor stars. So they're among the oldest stars in our galaxy. Now they orbit the galaxy in a halo. They go around and around the center of the galaxy in their own orbit. Okay. And I like the second camera because I can actually do some visuals. I know the camera doesn't have the same frame rate, but it's pretty good. And let me know, by the way, if you see any kind of issues with the stream, unless if it's doing any stuttering or anything like that. So these stars are metal poor. They're among the oldest, as I said. It's 31,000 light years away, which is meaning to say that the light we're seeing from this left it 31,000 years ago. Think about the history of our planet 31,000 years ago. So, we count human history as having started when we started recording history. And that's debatable as to when that was, but it's anywhere between 50,000 and 80,000 years ago that we actually started recording human history as a species. So I think it's interesting to see that the light from these stars has been heading toward us from all that long ago. So the cluster itself, as some of you may already be thinking, the cluster itself might not even be there at this point. It might look very different right now. So I think that's pretty cool. Now, if we come out of this, I'd like to take you up to another guy that we saw before, and I want to remind you of what this was. Okay. I got a few bugs flying around in here, which is kind of funny. Okay. You can see this object right now on the screen. It's a little bit faint, but we're going to fix that by taking a picture. I've got the alignment of the scope now so that everything shows up pretty much in the center where I want to go, and let's just hope it stays that way. This guy you've seen before, this is in the constellation of Lyra, which is the Lyre, or the little harp. And Lyra is an interesting constellation because it's very small, but it has a star in it called Vega, which is the bright one, and Vega and another star in something called Cygnus the Swan, and another star in Aquila the Eagle, all right, make up what's called the Summer Triangle. And within the Summer Triangle, that constitutes the constellations of Cygnus the Swan with the bright star Deneb, Lyra the harp with the bright star Vega, and Aquila the Eagle with the bright star Altair or Altair. And those three constellations have a wealth of galactic wonders in them, and it's fun to go zipping around those. I've spent nights just looking at Cygnus alone because there's so many things in Cygnus. Now as it gets higher in the sky, we're going to be able to see some really cool things. And also, as we're looking at the live view here, keep your eyes open, because every single time I've done this, by coming out here and just like running the telescope, whether I'm streaming or not, I've had something fly through the screen, like a satellite. So let's do a 6-second photo at a sensitivity of 10,000 of this guy that we see in the center here. So the screen goes black for a few seconds, and then when it comes back, boom, we've got an object that we can see. And this is the famous Ring Nebula that we've talked about before. And the Ring Nebula is actually a remnant of a dying star. Now, the other night when I took a picture like this, 6 seconds around this speed, it had a big blue background. Notice that now it's a little better, even though Lyra and Cygnus are a little bit low. They're not nearly at the top of the sky right now, at the zenith. So you can see that, and that's a shell of gas that's coming off of a dead star, a star that has dying. It's in the process of dying. And you can see a little tiny white star in the center. That little tiny white star is actually very hot. and it's got a lot of energy that it's throwing off, and that energy excites the atoms in the shroud of gas and dust that have sloughed off of this star. And those atoms of that gas absorb some energy and then immediately emit it back out. And based on the colors, we can tell what kind of atoms they are. All right, so we have oxygen, we have hydrogen, and a little helium. I mean, we have several chemical components in that gaseous cloud. And so it looks like a ring, and I mentioned this before, but now I can actually show you with a little camera. You know, here's my hands. Okay, when you look at something face on, you are looking through the front of your hand. Okay, let's look at it that way. But on the side, you're looking through more stuff along the side and along the edge here. So you're seeing through more. And then on the back side, you're seeing through less. And as it comes around again, you're seeing through more. So no matter where you are in space, this will always look like a ring. Now, there is some excuse me, there is some recent research that indicates that maybe this is also what's called a bipolar nebula. Bipolar nebula is something that occurs with these types of nebula, and I'll tell you the type of this nebula in a minute. But this type of nebula is called, possibly called a bipolar nebula, meaning that out of its north and south polar regions, we would actually see gas being emitted in that direction, that general direction. Now, some of these actually look like hourglasses. Say out of the north, you see a big, spew of this cloud of gas, and out of the bottom you see it, and around the middle you don't really see much. That's just how it looks. I'm not exactly sure how the bipolar nature occurs in some and not in others. I think it has to do with the rotation rate of the star, how energetic it was before it began this process of star death, and it's actually it's a process that actually has so many factors that we're still researching what those factors might be that causes a bipolar nebula versus a different type of planetary nebula. So when I look at this, we're looking at it as a right now a possibility that it can be bipolar, well, like people, I guess. Except bipolarity in the nebula world just means that it has the ability to show a variety of properties that make it look like an hourglass, where it's mostly emanating from north and south. My camera battery is dead. I'm going to change it, so you'll see that my image stays on the screen for the other camera, and I will put this one in. Okay, now let's go back. Okay, here we go. Alright. And I have to go back to the ASAs that I was at. Gotta change those back. I didn't remember them. And then go down to this. There we go. Okay. So, that was our friend the Ring Nebula once again, as I said before. So now, I think that taking advantage of the dark, I'd like to actually take us to something else. Now, everything we're looking at is within our galaxy. Our galaxy is basically, a term that I like is, our galaxy is an island universe of stars. And kind of isolated pinwheel of stars in space, all rotating around a common central core. And then we have several sister galaxies in what's called our local group of galaxies. One of those galaxies is 2 million light years away from us, and it's called the Andromeda Galaxy. Some of you know about the Andromeda Galaxy and have heard of it. Well, Andromeda is one of the galaxies within our local group. Also, the Milky Way has an interesting pair of galaxies that are in attendance, and they're right outside the Milky Way. Those are called the Large Magellanic Cloud and the Small Magellanic Cloud. These are two additional tiny little galaxies that are with us. Now, if you look at the Andromeda Galaxy, you see that the Andromeda Galaxy, if those of you that know, the Andromeda Galaxy, and it's not up now or I'd be showing it to you, the Andromeda Galaxy actually has two small elliptical galaxies that are on either side of it, and it's right in the center. And it has two of these elliptical galaxies, which is kind of interesting because we have two of our own, but they're they're kind of close to us and close to each other. A really fascinating pair. So I think that's really cool, and I'm gonna try and find us one other thing here. Yeah, see, it says the Andromeda Galaxy doesn't rise, you know, for another 30 minutes or 35 minutes, and it'll be fairly close to the horizon for quite a while. Well, we'll figure it out. We'll get to it. Let me see here if we can. Where is this guy? I was looking for another cluster, and it's fairly low, so we're not going to be able to look at that one. When they're low in the sky, it really kind of ruins the it ruins your impression, because you'd like to actually see what's going on. You like to see something clearly, and it doesn't work. You know, when we have something that's low to the horizon, there's too much sky, too much atmosphere between us and the object. More atmosphere will tend to disrupt the object more, and that's a problem. We don't want that. Okay, I'm going to go to one that we have seen before, but it's going to be better tonight. It's going to be much better tonight because the moon hasn't risen yet. No, it hasn't. And it's past full, so we're on the downside, so this is a good thing. Okay, moving. Okay. I don't see it in the view, but I will take a picture because I don't doubt that it's there. Let me see. This will be 4 seconds at 10,000, just to make it a little quicker. Look at that, right in the center. Holy cow, that's nice. Let me show you that again. Okay. This galaxy is actually called the Whirlpool Galaxy. We've seen it before, but we haven't seen it with this kind of clarity. It wasn't, you couldn't see it quite this way. And by the way, moving forward here, I'm going to try and have live image processing, so we can actually see this, the image processing process, so to speak. And so you'll actually get to see in more detail what this looks like. I can do it now, but because I'm the only one running everything, I'm doing 5 things at once. That would be it's an extra burden to go over to the computer and get stuff to work on that right away. Although I'm really tempted because this is a beautiful view. I'm gonna actually take another photo to show you. We're gonna take another one, and this one will be 8 seconds. And I'm going to drop it down to 4,000, so I'm going to go to 13 seconds. Now, it won't look much different. Okay, it's going to be 13 seconds, alright, at 4,000 ASA. Now, for every drop in sensitivity on the camera, it's called the stop, you raise the exposure by 1 setting, and that is equal. So it's a 1-to-1 relationship. So what you just saw didn't look much different from the previous. Okay? But the one thing that does look different is it doesn't have as much noise in the image. So if we zoom in a little bit, you can actually see now that even though there's some red dots, those spiral arms in the galaxy are showing up really nicely. And if we take the risk of going a little longer even, and I say let's go to a full 20 seconds, all right, which is actually 2 more stops for the camera, and then we just drop the, or let's just raise the ASA just for fun. We'll go to ASA 5000 and we'll do a 20-second shot. So now for the next 20 seconds I'll just do a song and dance, dun, 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 dun. And as we go here, you'll actually see the result. 20 seconds brings in more light. ASA that's 5,000 is a little noisier than 4,000, so we'll have to deal with that. But the result is just beautiful. Yeah, look at that. So the background looks a little red, and that's just because of the camera. And I can remove that, you know, going forward I can remove that. But check that out. You can actually see those spiral arms. You can actually see there's knotty detail inside those spiral arms. And that central core of the galaxy, that central core is actually an area in the galaxy where the stars are really compact and compressed around each other. And we think that there's black holes in these galaxies. I mentioned that before. But you know, we think that there's black holes in there. So I think, yeah, I was dancing, Amanda. That was me. So I'm not sharing the dome with anyone tonight. So we think there might be black holes in all these galaxies, including our own. And the spiral arms, you see how they trail off and they spin like a little pinwheel. Well, we think that gravity has an awful lot to do with how they're shaped. We think that there's rotational motion that goes into making those spiral arms, and those spiral arms are areas where you can see them because those are areas where star formation took place. Something had to cause gas to compress in a spiral arm manner within galaxies, and there have been all kinds of theories to explain it. Some are called, you know, there was one theory called density waves, which actually went winging through galaxies, including our own, and they would actually create a compression front, so to speak, of gas, and this would form stars, which would then form the spiral arms that you see. But it doesn't explain star formation in elliptical galaxies, which actually are just big amorphous round blobs full of stars. So you know, it's a different thing, and we don't know what that's all about. Now, as far as the Whirlpool Galaxy, just to give you a little info, the Whirlpool Galaxy is actually 28 million light years away, as opposed to, say, the Andromeda Galaxy, which is 2 million light years away. This is 28 million miles away. Okay, so it's more than 10 times farther. So we can see it like this in such exquisite detail because it's face on to us. It's facing us. This gives us something interesting. If you notice in the picture, in the center you have the center of the galaxy, and then just to the lower right there's a star. Well, that star is in our galaxy. That's here, and it's superimposed on that galaxy. But we have seen bright bursts like that in this galaxy twice in the past. They were supernovas that were occurring in that galaxy, one after another. And it's the supernovas which create the heavier elements in the periodic table, because it goes up to iron, which is 26, and then after that those elements are actually made in supernovas, except for the synthetic laboratory created elements that we have here. You know, you don't get Einsteinium and, you know, Rutherfordium, okay, things like that, but you do get all the other elements after iron, which is 26. So this galaxy affords us that opportunity because it's not obscured. We don't have anything obscured. It's face on, and that actually it's a pretty target. It's a wonderful target for amateurs with their telescopes to actually, you know, go there. They love it. And by the way, I'm sorry I didn't really announce the stream on my Facebook page. I figured I'll just go for it because the moon's gonna be coming up at some point, and you know, it's really pretty out there, let me tell you. So I want to just give you the best that I can do right now. Let's see. I want to show you something that we haven't seen yet. Dun, dun, dun. Okay, I'm looking at the time and I'm measuring it against the available objects because I want to be able to show you these things. Technically it says the moon should rise already. I don't want to see that. Hold on, let me just look. Oh yeah, it's down there. But you know what? I think if I were to go to the moon right now, I think what we'd end up seeing is a tree partially in the way. But we can try it just for fun, just to see what we get. So let's go check out the moon right now, because it's just rising. Moving. Oh yeah. I want you to see the orange color. Isn't that pretty? That is really pretty. Now it literally just rose, so it's not going to be clear. It's going to be fuzzy, but this is what you get. This is what you get. Isn't that something? But I want you to see the color because I think it's really pretty with the color. And we'll take a picture here just to see what we can get for fun. I'm going to drop the sensitivity down of the camera all the way to 100 and then go up in the exposure in the equivalent amount. So now we're going to take image at 0.8 seconds. Alright, here we go. And boom. Well, there it is. There's your moon. Actually, you didn't see it. I mean, it did. That's the image that it took, actually. So we got this beautiful moon. You can actually see it's not full. It is actually past full, which is great. It means the shadows will start coming back. Tell me what you think of that moon. I think it's pretty. I think we got that was a success. I think that's successful. And while we're staring at the moon, and you know what? I'm also Keith from P&K Space Imaging, who is our partner with all this. Keith and Paul are going to assist me in getting music at some point, because I do want to actually have music playing while I'm actually doing these, because I've done lectures all over the country, and I always, for the conferences they don't let me do it, but whenever I do private lectures I actually play music softly in the background, and that actually helps set the mood. It's really just it's all about the experience, and it's a really wonderful experience if the music's playing in the background softly. Not to be, to overtake anything, but just to be part of it. So you keep looking at that, and I will look for some more stuff for us. Okay, I'm going to check and see if that's something that we can see. Oh man, that's beautiful. Before the moon gets too much, and we'll come back to it, I promise, but before it gets too much, I want to try and get to this cluster of stars. actually, I'm gonna change my ASA again, my sensitivity settings. Alright, we'll go with 51,200, and I'll do just for fun, I'll do a 2.5 second exposure at 51,200 ASA, and let's see what we get. Wow, see what happens when it's low to the horizon? That was a cluster of stars in the constellation Scorpius, the Scorpion. And when that gets a little higher, that'll be really pretty. That's actually called the Butterfly Cluster. And it's a beautiful cluster. And its distance from us is around 1,600 light years. So it's actually pretty far away. But you can see how spread out those stars are. Now, they're spread out because after they formed, they were able to migrate away from each other. So I think it's kind of interesting because that's what happened to us when we formed, in our cluster that we formed in. And you might have remembered me saying the other day that we actually may have formed with the stars that formed the Big Dipper at one point, which is why they're all so bright compared to our planet. You'll also notice that in this cluster that there's a very bright orange star. You see it to the left. That's interesting because typically cluster stars are pretty much the same type of star. It's the same amount of gas that's available, the same amount of energy that they put out typically. But here we have different stars. So it's kind of interesting that we have that going on. And so it doesn't mean, in fact, that orange star is even in the cluster. It could be much farther away or much closer and not actually part of it. But we don't know. All right, I don't have a value for that distance right now. And the other thing is the estimates of the distance of this cluster have actually varied over the years. So it's not as simple to figure out as you might think. Now, the orange star that you're seeing there, all right, is an interesting star because it's actually a supergiant, and that supergiant star has reached the evolutionary place where it's begun to swell up large, and it swells up when it runs out of fuel, like hydrogen, and then it begins to contract as it runs out of hydrogen. After it contracts to the point where it gets hotter and hotter and hotter until it can burn other elements into other things. Among them, it'll burn helium into carbon and nitrogen and oxygen. And then it'll begin to swell again. And when it does that, it gets larger and larger and larger. It gets so big that in the end, when it runs out of those materials, the star begins to shrink again, but the outer envelope of that star is not necessarily gravitationally bound anymore to the star. And the radiation pressure that's still there can push that gas away, and it would slough off those layers. Where else have we seen this just tonight? The Ring Nebula. In that Ring Nebula, that little smoke ring that I showed you before, that same thing happened at one point during that star's evolution, and it left behind a hot white dwarf in the center of the star, in the center of the nebula. And this star is still a supergiant. It hasn't gone to the white dwarf stage. It may go there, or it may actually become a supernova someday. It depends on the mass of the star. And we'll talk about, in a future stream, we'll talk about stars and how they become supernovas. Because as the summer approaches, we have some beautiful remnants of supernovas that we're going to be able to see. And that is pretty cool. And I think you'll like that. Yeah. So, this is the butterfly cluster. So now, I want to take you to And I'll do that in just a sec. Okay. This next cluster is a little higher, but it's actually not. There it is. It's not. It's not high. As high as it could be. And I'm going to do 2.5 seconds at. I'll drop this ASA. I'm going to drop the sensitivity down to 16,000. Okay. I love these cameras. I'm telling you. So this is 2.5 seconds at 16,000. And let's see if it's too bright. No, that's nice. Okay, this is another example of a cluster. All right, and this cluster is also, it's actually called Messier 23. So again, it was the 23rd object that Charles Messier in the 1700s decided was not a comet, and thus don't pay attention to the star. Pay no attention to this cluster over here. It's not important. But this is not, it's not very bright. Very bright would be, when we talked about magnitude or brightness, very bright would be 0, like Vega. This cluster of stars is 7th magnitude overall, meaning that all together they only add up to 7th magnitude. So it's pretty, it's not that bright, but again, notice that there's different colors in this star, in this star cluster. And if I come out, you'll see that this is how it looks live. And the live view, you can tell. I mean, this is enhanced. Trust me, this is at 16,000 sensitivity. Let's take a look at what it would be for your eye. Okay, if we went just to your eye, okay, then it would be kind of like, it'd be like this. Okay, you'd see that bright star in the upper right, and that's about it. All right. So really, we actually these cameras allow us to actually see more than the human eye can see. So this is the cluster that Messier 23. Again, these stars were all kind of born close together, and then they migrate apart through mutual gravitational pulling and tugging and whipping around. And the stars evolve. They evolve when they use up their first chemical base of hydrogen. They start burning helium, and when they do that, their color can change, and their spectral class can change. How we classify them changes depending on what they're burning for fuel. So a number of these stars in here are different. You can see there's some orange stars. There's actually some blues, and the star there on the upper right in this image is actually a star that's not in that cluster. It's actually a different star altogether. So that cluster of stars is there. Now, what's interesting here is when this gets higher in the sky, we'll be able to take other photos, and you'll be able to see that it's in the middle of a star cloud. You can see hints of that, and you can kind of see that there's some darkness over to the lower left of that cluster. Okay, that darkness that you're seeing there, okay, that's really there. That's part of the naughty collections of star cloud stars that we're seeing. And as we go further, we'll be able to take more imagery. I'm going to just, for fun, I'm going to see if I can, at ASA 16,000, I'm going to take a risk and do a 10-second photo just to see if we can see a little bit more of this. So we're going to try and dig into this cluster a little more and see some more detail. And hopefully we will. The moon is rising, but it's not terribly bright yet. But it was bright enough, as you could see. Yeah, we didn't get it. We lost it. We don't have the opportunity because we don't have that. Now, you're going to notice also there's some interesting elements in there too. If you look really close, you can see some of the stars that look like little tiny pairings of stars. Those may be binary stars, or they may be, one star closest to us and one star a little farther away, but next to each other in the cluster from our particular vantage point. So these are really cool, and if you get a chance to get a telescope, these are called open clusters, all right? They differ from globular clusters. We saw earlier, globular clusters are tight balls and they look like exploding snowballs of stars. Open clusters are more open, of course, and the stars have the ability to migrate away from each other. Some open clusters are very tight, and some clusters are not. And to give you an idea of a very tight cluster, I want to see if this one is available. I'm going to show you one that I might consider very tight. Hold on. Let's go see. Okay, let's go to this one. Let's go see if we can get to this. Okay, moving. I know, I didn't have the live view on, I'm sorry. Right there in the center, and it's moving a little bit off center. Okay, this is called the wild duck, and don't ask me why. I don't actually know how the name wild duck occurred. This is Messier 11, and we're going to take a 4-second exposure at ASA 16,000. Then we'll take another one a little after and make it a little better. Now, check out this cluster. This is, let's go to the view here. This cluster of stars, you see, it's in murk, so that's why it kind of looks a little wacky like that. It's really not that good. It's actually, let me go look out of the dome for a second here. Okay, it's actually in a little bit of cloud that's over just above the moon. So the fact that we can see it at all is amazing. But the wild duck cluster is pretty cool. I mean, it's actually 6.1 kilo light years, okay, or 6,100 light years from us, and that tells us, in fact, when we look at it, we can actually, if we know how far away it is based on the stars that we recognize and we can get distances to in the cluster, we can then measure the size of the cluster and figure out what it looks like. But we're only the reason we want to look at this is when we look at the full moon and we look at this cluster is like 1/3 of the size of the full moon in the sky. So it's a big cluster at 6,100 light years away. Okay, so I think that's still pretty. That means it's pretty big out there in space. And if you're in the middle of that, you probably wouldn't even notice, that the stars around you are any brighter or any dimmer, because you'd be in the middle of it. And the universe and the sky is very, very big that way. Now, I'm showing you this cluster because, even though it's in the murk, because when we looked at globular clusters before, and I'll show you another one just after this, just to show you. When we look at globular clusters, we actually see that those globular clusters are very tightly bound clusters of stars, as we said. This was mistaken as a distant globular for a long time, until they got the distances to it, and they realized, oh, that's not a globular at all. That's actually just a very tight open cluster. So this is an example of an open cluster that's fairly tight, and you just saw one that's a little looser, and then we saw one earlier that was actually looser than that still. So these are the kinds of things that we see, and it's sort of the anatomy of these types of clusters, open clusters that is. So let's now go, we'll go back to the live mode here. Let's go check out one that we've seen before. Isn't it great how it just like zooms right into the center? I mean, this is really, really good. Okay, this is a globular cluster, and this globular is Messier 13, one we saw before. Now, we could do a tour all night long of just globulars. There are so many of them. Again, Messier 13 is sitting really, really far away. It's actually, at a distance of 23,000 light years away. And if we want to just take a quick photo just to show you, this will be a 4-second at 16,000. You see how much you see of it there. Now watch how much you actually see of it when when the photo comes in. You see the difference? Okay, so there's the live view, all right, and here is the photo view. Look at the difference. So there's that many more stars that you just don't see, and when you look at it with your eye, that's about what you see. Just like that. I've got this set up so that when we look at it with the camera in raw view, that's pretty much what you see with your eye. No more and no less. Alright? But then the camera gets this in just 4 seconds. I mean, I have to say, that's the special camera I'm using for sure. But this gives you a deeper look at what's out there. So again, that's what you see with your eye, and this is what you see with the camera. Alright? And Messier 13 again is it's a cluster of stars that are globular in composition, and they are metal poor stars, among the earliest stars formed in the galaxy, and they're on the outside edge of the galaxy, kind of going around. They're called halo objects, not like in the game Halo, but they're halo objects in that they are on the outside of the galaxy, orbiting the outside of the galaxy. In orbits, and there's many of them, and they have hundreds of thousands of stars, have tens of thousands or 100,000 of stars, and this one is one of the best in the sky. In the north, there's actually there's actually a much better one in the southern sky. It's even bigger and brighter, and because we can't see it, it's like, well, we got ripped off, but it's okay. Not worried about it. So let's see now. I would like to take us to another object, and we're going to go here. We're going to go to an island universe of stars, and this island universe of stars is something that is called the Spindle Galaxy. So we're heading there now. Moving. I'm getting the faint objects in before we actually have to deal with the moon too much. All right, let me look out. Oh, yeah. Well, if it's in there, it should be pretty. Again, the photo we're taking of the Spindle Galaxy. You'll see why it's called the Spindle as soon as you see it. Okay, 4 seconds at 16,000 ASA. Dead center. So now I'm gonna drop it in ASA a little bit because I want you to be able to see it a little better. So 1 second. We're gonna drop to 8,000 ASA, and we're gonna take a photo that's say 13 seconds. No, 15 seconds. I don't know how this will come out. I have a suspicion though. So this particular object, the Spindle Galaxy, is really interesting because it's kind of edge on to us. So we're looking right at its disk, edge on. And this galaxy has a dark lane of gas and dust right through the middle. And that's what we see. And you can see it here. It shows up very nicely. So I don't know if you can, I think you can see that. You actually see what looks like a line through the middle of the galaxy. That's actually the dark dust in that galaxy. And it's 47 million light years away. Again, remember, Andromeda Galaxy is 2 million light years away. 47 million light years away. And so this galaxy is actually really just a splendor in the sky to see this. And it's actually got a lot of stars in it, probably several billion stars. Okay, we have between 100 billion and 400 billion stars. We're not a small galaxy, actually. We're pretty big. I'm just gonna pull up my seat here for a minute because I want to be able to talk to you about this. So when this guy was first found, you know, they knew enough about galaxies to know that you know, you'd see gas and dust like this in these galaxies, but they're interesting because we actually can see the morphology of these galaxies. We know what's happening with these galaxies when we look at them. Okay, I'm actually going to take a 30-second exposure at 2500 ASA. So I'm dropping it down a lot because I want to see if I can get a better view for you of that dark dust. They're called dust lanes. The dark dust lane. Oh, Starry Night. Yeah. You're welcome. I'm glad you like it. All right, let's go. Let's get close. Let's get close and see what we get. Look at that. See that? It looks like a UFO. You know, but you're seeing that dark dust lane going right through the center. Now, there's a technique that I can't do live with you here, but I can show you the results when I get it done, and that is called stacking. What I do is I take about 25 photos like this, 25 30-second photos, and when I do that, you actually you have a lot of the signal, that is the stars and the dark lane and other stars in the view, and that signal is enhanced against the noise, which is the reddish and the other, you know, features you see in the black area. Okay, so you know, this is you know, far and away the better way to do it. By taking a singular picture like this, we get a pretty shot, but we don't actually get the best view. To get the best view, we actually would have to stack a lot of images and then do that, and we'll do that. I'll show you the results. You know, when I get to it, I'm going to stack a lot of these pictures and show you the final results, so you can see just what you can do with an observatory instrument like this. So this galaxy, as I said, is 47 million light years away. The other stars you see in the field are actually what they call field stars. They are in our galaxy, and we're looking past them by millions of light years to see this galaxy out there. And those stars might only be a few thousand light years away, and the galaxy is 47 million miles past them. 47 million light years past them. So it's really neat, and I think that you know, this is pretty cool. Now, I actually do have the chat up here, and Daryl's asking if this is NGC. Let me see on the screen here. 4560. No, this is actually NGC 5866. It's also NGC 5933, 53, sorry, 53, no, that's PGC, sorry. It's NGC 5866. It's not 4566. But that's okay. You know, you can be forgiven for not knowing the NGC numbers. I don't know all the NGC numbers. I just know cool objects, and I know them by their scientific relevance. I may not know them by this, so that's my mistake if that's the case. Okay, wait, I'm seeing something in the chat here. I just saw it was in red, and I think that it's, sorry about that noise. Ken, the question was for you. What question? Oh, okay. No, I don't know what question you were asking me. Sorry about that, I don't see it. Hawkeye, Keith sent you and told you I need to get him a beer? Or is that to me, or is that somebody else? Well, anyway, that's what I love about chat. You never know who's talking to who. If you're talking to me, let me know by putting my name in there, so I know you're talking to me. If you're talking amongst yourselves, then I won't interfere. You know, and you're doing a good job, you folks out there. And I have some mods out there. I saw that Amanda was here. I want to thank you for being here, and Rockstar is here. And he's able to, you know, kick anyone out as well if they're, you know, mouthing off. But I haven't seen any of that so far. It looks pretty nice. Pretty good folks out there. So let's see now. I want to take you before the moon takes that away from us. I want to take you someplace else. Oh boy, I gotta show you that if we can see it. I'm gonna go check. I'm gonna look out the dome here, see if we can see something. Oh boy, we're gonna try it. Okay. We're gonna try and I'm gonna try and show you a star forming region. All right, and I hope that it's not too much in the murk. I know it is actually a little in the murk, so I'm apologetic for that right now, because it's my responsibility to keep these things out of the murk. You know, I just, you know, I can't do everything. That's a joke. All right. So, okay, moving. Live mode. Oh yeah. It's a little bit in the murk. It's looking down really low, but you know something? I'll give it a shot. I want you to see this. I have to wait for the telescope to beep. You'll hear it beep. Okay. I'm not going to take a 30-second here because we have the moon, but I am going to take 8 seconds. Now I'll go 10 seconds at ASA 2500. Ken, you asked me a question about putting the stars out of focus. With the galaxy, unless we really have very, very high power, galaxies always look like fuzzy clouds of gas and dust. You don't actually see the individual stars unless you really do high power and you do a lot of stacking, like I was talking about, where you put images on top of each other. If you do that, you end up getting a much better view. I know that, let me just show you this here first. Okay. This is what came in at 2500 ASA. That's actually called the Lagoon Nebula. It's Messier 8, and it's a favorite stopping point when you're trying to look for really cool things. I'm going to go up to 8000 ASA, and we'll do a comparison, same amount of time. Okay, 10 seconds at 8000. And you'll see it's going to be a lot brighter in the background because we have a moon out there. But let's see what our limits are. This is how you test. You go back and forth, you find the right exposure. Okay, so it's brighter, as I said. So that's 8000 ASA, 10 seconds. That's 2500 ASA, 10 seconds. Alright, and if we go and say go to, let's go to 6400 ASA, and let's go to 15, no, I don't do 15 seconds, that'll be bad. It's not quite high enough. You can see the stars are softly, when you look at them in live mode, they kind of are softly pulsating. That's the atmosphere doing that. And that's part of what's called atmospheric scintillation. And scintillation is spelled SCINTILLATION, scintillation. And it's a process by which the atmosphere disturbs point lights in the sky. Stars are point light. We don't see this on the moon except on the edges, where you see that rippling effect on the edge of the moon. All right, we don't see that on the moon because it's so broad and large. Let's just go back to this for a sec. I want to zoom in to show you. And the stars need a little focus assist. There's some red part of the nebula there, and there's so much more. This entire region is all red gas and dust. But with the moon like this, we can't really see it. And I did my best to try and get some of these faint things like the galaxies so we could see them ahead of time. So I do have the chat up, by the way. It's on the right hand side of my preview and of my view, and I actually have I have it set up so that most of the observatory can be seen, because I actually have a lot of the screen is showing, so I still can see, and you can see with the secondary camera. That way you know what's going on, even if you don't know what's happening. You can see that there's stuff going on, or I'm in here doing stuff. So that's that guy. That's the interesting thing about this nebula, M8, the Lagoon Nebula. It's a region of star formation, and you can actually see, if we kind of zoom in on these stars a little bit, you can see that there's a cluster in there, and this cluster is actually a fairly bright cluster, and the stars are quite young, and they were formed in this cluster, and they haven't moved away yet. They will eventually migrate out of here, all right? But they're still here in the middle of this cluster right now. So I like that you're getting to see this just as the astronomers see this. This is how we see it. We see these things this way, and we actually do our research this way. I'm kind of a little bit ahead of the game. I'm connecting Wi-Fi to the telescope, and I'm controlling it, via the iPad. I can actually go in the house if I want to. The only problem is I don't have the hookup yet to move the dome. But once I do, then the camera and the iPad and the telescope are all connected to each other, and I can control them all remotely. And once I get these remotes up and running, then we're going to be set to just do all this remotely. So that's why when I move it to Arizona, we're going to see it in the same way we're seeing it here, except 10 times better, probably maybe 15, 20 times better. But it's going to be pretty cool. I'm looking forward to that. And that's going to take some time, but I'm glad you're taking that journey with me, and I'm glad that you subscribe and are part of it. Let me see if we can find something else. I know that there's another object right nearby that we want to see, and I'm going to go there right now. I will show you. I know, it doesn't look like much yet. Let me take it down a notch and give you this get a little photo here. We'll go up to ASA 12,800, 2.5 second exposure, just to make sure we're where we think we have to be. And we are, but it's, again, the moon's causing a problem. Oh, that's too bad. Well, I was taking you to another nebula, but the moon is already too bright, and it's sort of a hazy, kind of summery night. It was 90 here today, and oh hey, see that? We caught the plane. That plane went right through the view. I'm glad we saw that. So I think that's pretty cool. Did you all see that? Were you looking at the screen when the plane went through? I don't know if anyone's seeing it. You'll let me know. Chat's a little behind. But you'll see, it was really cool. I told you, you gotta keep looking. Every night, things fly through. In this case, it was a plane. And when we're looking at a shallow angle like this is a shallow angle. It's more likely that we're gonna see these things, And when you go back when you go back afterwards and you go through this, you'll see that it's you can stop it and check it out and see a lot of it, and it'll make sense. You'll get to see exactly what it looks like, possibly even reflections with the moon on the bottom of the body. I've seen those before. Now the other thing is, you'll notice I'm moving around in here, and I've said this before, and you still hear me fine. It's because the room is round. It's a round dome, and the microphone's right here in the center. I've moved it to the center. It's no longer at the edge. So the sound is, I think, consistent, but you need to tell me that. I mean, if I get right up close, I mean, this is how it sounds, and it probably sounds fantastic this way. But when I'm out here, this is the working distance that I have to use. So it still looks good. Let me, I'm gonna just do a 5-second exposure at 12,800 ASA just to see if I can just pick up anything here to show you. Yeah, it's still dim, unfortunately. Yeah, as soon as the moon comes up, it's like, oh man. But there's a bright red nebula right there where those two stars are in the center. There's those two stars that are very close to each other, actually. Those are actually a pair that were born there, and these stars are very, very bright, and they're illuminating and causing the hydrogen gas in this nebula to absorb some of the light, and then they spontaneously give it back. And the radiation comes off at a certain frequency that we know as doubly ionized hydrogen, which is H2, H, Roman numeral 2, H, II, so to speak. And that is characteristic of star-forming regions. They always have that reddish glow. Raspberry Snapple break. All right. Now, let's see what we can do. And for the fun, let's go see. I'm looking for a couple here for you to. Looking for a couple. Hang on, I'm just looking for something. Alright, we can try that. Let's see where it is. Okay, we're moving now. Okay, this is not Albireo. That was that star that we typically go to for focus our telescope. This is not Albireo, which is in Cygnus. This is in Cygnus, but this is another double star in Cygnus, and it's called 16 Cygni, and it has a magnitude such that you wouldn't be able to see it with your eye in any but the darkest areas. And it's sort of in the northwest corner of the constellation Cygnus, and they actually are. This is 68, almost 69 light years away, and these two stars are actually kind of like the sun. And this is, I want to show it to you because this is 68 light years away. This is kind of what our sun would look like, except two of them. So let's zoom in on this. Okay, now we're going to just move it in to get it in here. Alright. Hey, stop. sorry, it's starting to do some crazy stuff, starting to move around. There we go. Okay, now I'm gonna do a little focus on this. Okay. So now I'm gonna take these out of focus. Okay, and two things. First thing is you can see the colors, and the stars are actually these stars are actually very these stars are actually more white, although our sun is actually typically fairly white, believe it or not, and it's only in the atmosphere that it makes it look redder and yellower. It's more white than that up in space. The second thing is you can also see the disturbance caused by the atmosphere. Starlight doesn't fluctuate like this. This is not how starlight looks if you're out in space. Stars are constant unless they're variable stars, in which case they can change their brightness spontaneously in a variety of ways. Okay, but this particular pair of stars, as a double star, as I said, they're almost 69 light years away, and it's a special star because this particular pair of stars actually has a planet around them. Okay, and it's a planet that actually orbits the fainter of the two stars, and you can see which one that is. Okay, let's just take it out of focus a little more here, and you'll get to see that. Let me just do this and get this out of focus for you. Alright, so you can see that the lower left star is actually a little bit fainter. This is another way to tell some information about stars that you just wouldn't ordinarily know, and that's you defocus them to see their color and to see which one's actually brighter. And it's that fainter companion there of this double star that actually has a planet around it. It's actually one of the few exoplanet systems we know that actually is in a binary system. I think it's pretty cool. There's only one planet so far that we've found in here. Now, the planet is actually circling that other that star at 1.7 astronomical units away from that star, which means that the planet is actually just a little farther away from the star than we are from ours. So perhaps it's just on the fringe of its habitable zone. But does that mean that life couldn't exist? Well, the other star, again, these are 69 light years away. That other star is actually going to be, several light years, a couple light years away from this other star. So it's very possible that there could be life on a planet there. All right, I think it's pretty cool. And this is a case where we actually get to see in real life a system that actually has a planet around it. And this is, you can't see the planet, of course, but we can see that lower left star. Notice now, as we look at that lower left star now, and I am zoomed in, of course, when we look at that lower left star, the one thing that you notice is that you can't really tell the difference in brightness, can you? You did have to take it out of focus to actually do that, which is kind of cool. We had to do that. So I hope you like that little side trip we took to show you that, because I wanted you to see the I wanted you to see that we actually had a system that had an exoplanet around it, because that's something that we haven't talked about, and that's actually my specialty, our exoplanets. So that was my little treat for you tonight. Let's see now. Yeah, there's several asteroids that are out there, but we wouldn't be able to tell the difference unless we took photos over time and then compared the photos to each other. They'd have to be taken like an hour apart to actually see them, which we can do. and not tonight, but I mean, we could do this at some future point. We could just say, we're going to do asteroid hunting tonight. We'll just take a series of photographs over the course of the night and go back to the same place and retake photographs and see what we get. And we might actually be able to compare them dynamically and say, hey, look, that's the asteroid, we can tell. I don't know if you were in the P&K Space Watch when Paul brought up Pluto, but Paul did bring up Pluto one night, and you could see it. It was clear. You could tell which one it was. So, if we can see Pluto that many billions of miles away, we can see an asteroid that's you know, a little bit smaller, but a lot closer. So it's very possible. So let's see now. Let's look again. I'm going to check this one. Well, is that where I want to go? M23? Or did we do that already? Did we do that? I think we did this one. Sorry, I've got but with the slit open on the dome, I got mosquitoes flying around here, and I already zapped myself with, you know, bug stuff. Now what I'm going to do, I'm going to take you to this other nebula, and we may or may not be able to see it because of the moon, but it is fairly bright. So I'd like to go there if we can and see what we can say. See if we can see it. Alright. Okay, now we're going to be moving. We do have some glow of the moon there, there's no doubt. But let's give it a try. 5 seconds at 12,800 ASA. Let's see what we can get. This one's fairly close to the moon. Yeah, it's not terribly, well, you can sort of see it. I don't know if you can see, but across the center of the field, and it's sort of on an angle from the lower left to the upper right, in between the sets of stars, there's actually a reddish nebula there. That's actually called the Omega Nebula, and it's interesting because it's 4,200 light years away, and it's another star-forming region, and it's within the rich star fields of the Milky Way, and it's another favorite haunt of mine when I was a kid, looking with a telescope. And right now, like I said, with the moon, it's not really conducive to getting a good imagery. But I did want you to see it. These are the star-forming regions I was telling you about that are so important to our understanding of what goes on in the universe. So I'm going to just, for fun, I'll take 10 seconds at 8,000 ASA. It's probably going to be bright, and the brightness might overwhelm it. But this one you can actually see with the naked eye, believe it or not, if you know where to look. Alright? Yeah, I mean, I have to get some dynamic image processing here to show you, because this is, I could just, in 2 seconds, I could show you how this actually can be seen a little better. And just because I'm trying to, just because I'm trying to do this, let me just see. Bear with me for 1 second. Will I be able to actually do this? Let me find out. First thing I would need is to make sure I had that. I got that on here. But I have to be able to get the image off the camera, because it's not here, it's on the camera. So to get it off the camera would take a little extra effort. But boy, oh boy, if I could figure out a quick way to do this. All right, I'm gonna figure this out at some point, like probably tomorrow. I'm gonna figure this out because I really do want you to be able to see this. Absolutely do. Yeah, the moon stinks, Dave. I mean, it's great because without the moon, you know, a lot of things wouldn't have happened the way they did. You know, we wouldn't have, you know, we wouldn't have evolved exactly the way we did. But I'll tell you, it is interesting that we have evolved to where we are. So note that nebula. You can see it's faint only because of the moon. If the moon wasn't there, I could actually, this could look so much brighter. But you can see it. It's right there in the center of the view. Without any question, it's there. Again, it's the Omega Nebula, and it's 4,200 light years away. It's a star-forming region, and it has a lot of cluster stars associated with it. You can see up above there. And I'm very happy that we could at least see a little bit of it. I'm going to take you to another one, which is, it's actually kind of famous, and as long as we can see it, and we will, okay, and this one, moving, this one is called the Eagle Nebula, and the Eagle, all right, is associated with that cluster of stars you see in the screen. And it's here that, and you actually, you know, all of you know this region very well, and you just don't realize it. This is the region where the Hubble Space Telescope took that image that's called the Pillars of Creation. Okay, so this little cluster out there, I'll do it in 10 seconds at 8,000 ASA. This little cluster out there of stars has some nebulous clouds associated with it, with gas and dust. There's also dark globules, they're called dark globules. And of course, you know, again, with the moon, we don't see them. And that's, I apologize for that, I wish we could see them. But either way, we're seeing these beautiful clusters that are associated with these, and I think that's important too. So you're seeing the cluster stars associated with the Eagle Nebula, and the Pillars of Creation are actually wound in among those stars. And when we take a nice longer exposure without the moon, we'll be able to see them. But it's not a waste, and it's not a bad object, because we're actually seeing it now for what it would look like to your eye almost. You know, you don't, the nebulous detail is not evident to your eye. And when the moon's out, I can't really take longer exposures than I am for, you know, without losing detail or without it turning very, very bright. So as the days wear on here, if I get a couple more nights of great seeing, and the moon is not up, because as we go on and on and on, the moon rises later and later, and we'll be able to look at this nebula again, and you'll see a much different scene than we're seeing here. So it's much prettier. But again, it's a star-forming region. It's a famous one because the Pillars of Creation photo that the Hubble took is in here, and this object is actually 5,700 light years away from us, and it's a very fairly bright as far as nebulas go, and it's a very fascinating location. If only we could see it a little better. But that's all right. I'm okay with it. I really am. Now, let's just do, because we should, let us go to another object that I know you'd like to see. I know you'd like to see this. Alright, just a second. I'm queuing it up. Queuing it up, just a sec. Here we go. Okay, here we go. Yes, it's the Great Oval Constellation. No. This is actually an overexposed view of Saturn right now, and it's overexposed because I want you to see the moons. Alright, and you'll see that there's a, let's zoom in a little here. Okay, I took a shot, and it's going to be a long shot, and it's set up, so my apologies. Alright, but let's take a look here. Here's the image. Now, that's Saturn you're seeing right there on the screen, of course, but you don't see the rings yet because, first of all, it's low, and I can change it so you can see it, but what I want you to see is that when we zoom in on this here, you see there's like 4 moons that are close to the left side, okay? Those are starting at the upper right, that's Enceladus, and then down below, that is Tethys, and then to the upper left, the topmost moon that you see there, that is Dione, and then we have Rhea, and then we have farther to the left over there, the brightest one, that's actually Titan. And you'll notice Titan looks a little bit orange because it has this orangey nitrogen atmosphere, and it's kind of fascinating to see Titan like that. Now, if I actually want to see it, and get it looking like it should, then we have to drop the ASA, the sensitivity down, and I'll bring it down to say 320, and then I'll change the settings here, and now if I zoom in, okay, now you can see it when I get it in here. Hold on. There you go. So there's Saturn in the murk. Alright, and again I'd have to bring the exposure, make it a little bit longer so you can see the moons again. But there's Saturn, and I think over time I'm actually going to find a way to do what's called eyepiece projection. I already can, but it doesn't give me any dramatic effect here. So I'll have to take care of doing that again. Wait, what am I saying? Oh, okay. I saw something, Amanda had written something in all caps, and I think maybe she just had her caps lock key on by accident. Okay. So Saturn's in the murk, so not much to see. But you have to admit, it's a gorgeous planet. And, you know, I think it's important to talk about the rings. Because we see it with rings and we just assume, oh, it's the ringed planet. But do you know anything about the rings? Do you know why the rings are there? You know, Saturn has, you know, over 65 moons, you know. And so you have to say, well, why did the rings form? What are those rings from? Well, Saturn also has the second largest gravity in the solar system, besides the Sun, of course. Jupiter being the largest planetary gravitational well. Saturn has the next. And but Saturn's density is fairly low, and it would actually float in water if you could put it in water, okay? But it's massive overall, so it has massive gravity. So anything that gets close to it stands a chance of being torn apart. And it's possible that there was once a moon that either was captured by Saturn or formed near Saturn, and as it migrated closer to Saturn over the course of its lifetime through gravitational interactions with the other moons that were forming, it's possible that it got within that special limit called the Roche limit. And when it got within that limit, the gravitational tidal forces on one side of the planet versus the other side, one side of the moon versus the other side of the moon, were too much and ripped the moon apart. And so the moon would get pulverized. So I think that's a pretty straightforward approach here to look at for Saturn. Now, the ring colors are due to the fact that we're seeing reflected light, obviously, off of the particles in the ring, but they are yellow, aren't they? They have an interesting yellow color. Now, they are reflecting sunlight, but that's not reflecting yellow because it's the sunlight. It's reflecting yellow because the particles in the rings are of that color. There is a color in the rings that are like that. Now, the cloud bands on Saturn, like Jupiter, are made up mostly of hydrogen gas, and it may still have, like Jupiter, a liquid metallic hydrogen core. And when you say liquid metallic, it's like, what the heck does that mean? Well, under high pressure, the hydrogen in Jupiter, for instance, would get compressed until it becomes a liquid. And under very, very high pressure, it acts like a metal. It's like a metallic core. It's not a solid core per se. And so, for instance, if you were to fly a spaceship directly into the center of Jupiter, your spaceship would eventually collide with the core if the atmosphere didn't burn you up and the pressure didn't destroy you. And then you would be, destroyed, because it would literally be. It's a hard. It's a object that is much, much denser than the regular atmosphere. But once the atmosphere is, once you negate the atmosphere and you end up in the core of any of these planets, they are going to be this like liquid metallic hydrogen. And the cores of these planets are not as well understood as the other planets are. The solid planets, terrestrial planets, they're called. Or rocky planets, they're called. But even so, we have to look at Saturn and Jupiter and Uranus and Neptune, for that matter, for what they are. These are gas giants, and these gas giants were able to sweep our solar system of dangerous rocks that could have prevented us from getting as far along as we have so far. Just a few years ago, we saw Jupiter get hit by comet Shoemaker-Levy, and I actually watched this in this very telescope, actually, and I watched it. I watched the pockmarks appear on Jupiter's cloud tops. Black objects just boom suddenly appeared. I mean, it was beautiful. You just see them, and I couldn't believe that I was actually seeing it, but it was there, and I saw it. And I wish I was able to stream. Could you imagine that? What a stream that would have been! But alas, it wasn't to be. So this ring system we have around Saturn, like the ring system in Jupiter, which has a ring, the ring system around Saturn is possibly been created by a former moon that got into the Roche lobe, the Roche, and went beyond the Roche limit that we talked about, and caused the moon to break apart. And then over time, through successive orbits, collision of the debris would have caused a major malfunction in the largest debris. It would actually broken up into much smaller pieces and got pulverized over billions of years. And that's just what we see here. And then, of course, there were particles of ice and other stuff that was caught in here. So I think that's I think that's just what we have to think about with Saturn. Hang on, I'm looking in chat here. There's a question from Ken. Do you think there could be a way to play the rings and get an analog signal from them? I would love to know. I would like to know what you mean by that. Play the rings, like a record. Well, actually, you know, I have to be fair. That's actually not such a dumb question. And Ken said this may be a dumb question, but it really isn't. I'll tell you why. The radiation fields around Saturn, radiation fields around Jupiter, do cause interactions with particles, and they do cause sound. Not sound that you notice like traveling through the air, but sound that we translate from radio frequency disturbance that we get from the ring systems. Gosh, it was 1984. I actually built a radio telescope and listened to the moon Io, which is Jupiter's closest moon. Io was spewing sodium into space, and it has what's called a sodium torus, and that's basically a thick cloud of sodium that is around it as it's orbiting Jupiter. And that sodium torus makes a strange amount of noise, and that noise is picked up, and we picked it up with our radio telescope. So I think that, you know, that noise is something that we would end up having to be able to capture, listen to, track. And what I did was I actually ran that noise through filters, and I actually translated that radio frequency disturbances into sound that sounded kind of like this. It was like, if you want to call it music of the spheres, that's what it was. And believe it or not, that sound actually helps us. That sound helps us greatly, because it helps us figure out the nature of what's going on there. And based on the sound, you can tell how much is going on and when there's a lull. And it could be, depending on where Io is in its orbit, maybe it's being squished a little bit, and it happens more. Like Enceladus on Saturn is, as it circles, it's slightly an elliptical orbit, and as it orbits Saturn, you know, it actually gets squished a little bit at a certain point in its orbit, and not at another point in its orbit, and that's when those geysers spew the water ice that we've seen, and the carbon dioxide and the hydrogen that we now know is coming out. So I think that's kind of cool. So that said, I'm gonna just read another question here. Okay, basically, I think I'm kind of answering your question, Ken. I think when you're talking about playing the rings, not you don't mean playing the rings. I realize that, but you're really saying, is there a way to translate the signals we get from the planets into something that that we can hear? I know that, but then you also said, I just wonder if you could replicate the visual. I'm not sure what that means. Replicate the visual. You're saying based on, well, okay, you know what? I'll tell you what we can do. What you're saying actually is something that we have done. By listening to the sounds and translating the signals from the ring disturbances, we were able to find that Saturn's rings have more rings than we thought. So there's many, many rings, like the grooves on an old record player, an old record. We see that Saturn's rings has many grooves like that, you know, many separate rings. There's more gaps than were ever thought, and there's areas in the rings that are denser than ever thought. And there's weird things called spokes, and spokes, like spokes on a bike, are these radial shadow-looking objects which go the other way, like spokes do. If the tire is the ring, then the spokes go, you know, perpendicular to it toward the center, and that's just what we're seeing with Saturn's rings. Every now and then there are these spokes that are going toward the center, toward the planet, you know, at 90 degrees to the ring. And those spokes are, they look dark, and they are a function I believe, of what are called the shepherd moons. Now, within the rings shapes and types and divisions are maintained by these little tiny moons that are called shepherd moons. And Amalthea is one, and there's a number of many others. And these shepherd moons are actually the objects which actually shepherd or guide the ring particles. In some cases, and I got to do this as a visual, so I don't know if you can see this, but in some cases, there's a ring. Okay, there's my hands. There's a ring out here, and there is a ring here, and there's objects going through the rings. And at some points, as an object's approaching, and there's another object down here, the one that's closer to the planet is actually moving faster. And as it catches up to the one outside that's moving slower, what happens is they actually swap positions. And the one now that was above is now below and starts to move faster. The one that was below and moving faster moves up and starts to slow down. So they actually swap positions. I mean, that's the coolest thing. And that's been going on for billions of years. It's an absolutely incredible dance that these are doing up there. Let's see. Yeah, I see, Ken. I think you're... Oh, you do mean try and get pics and then translate it and play it like a record. No, that's nothing that we can do, unfortunately, because the information on vinyl is actually imprinted electronically through the sound waves that were played to get that sound onto the vinyl record. And with Saturn, there's really no rhyme or reason to that. We don't have a sound wave that originally put this data into the rings. So yeah, that wouldn't work, unfortunately. But I mean, there's no dumb question, believe me. I think that anything that we can try is great. But that one wouldn't work, unfortunately. I wish it would. But I just don't think so. Okay, let's see now. We got Saturn in here. I'm going to go to the moon, not because it's an old standby, but just because I want to show you the difference between how the moon looks now and what it was earlier. So you'll see that the moon will actually be a little nicer looking. So let's do that. So 1 second. And I'm going to pop off of Saturn here. I'm going to drop this down. And I will say, okay, and I'm going to say go to this. So we're now going to go to the moon. Okay, moving. Okay, so now you actually see that the moon looks a little bit different from before. And something else that I want you to notice too is that the moon actually doesn't look like it's smaller. It's actually the same size that it was when it was on the horizon. Yet to the eye, it looks bigger. So, for instance, when you see that, that's actually an illusion. The moon is not any bigger on the horizon than it is when it's up above. That's just strictly an illusion. And if you measure it, you will see that it's in fact identical. And that's just what we're doing here. And let me see if I can get a little closer, zoom in here, and then move us over and do some critical focus. Okay, that's actually pretty good, but I'm gonna do it anyway. So to focus, I take it out of focus and then bring it in. Oh, never mind. I like that. Alright, that's actually looking really good. And I'm gonna see, that's something we couldn't do before now, you see. It looks beautiful now because we're able to get it a little higher in the sky. Of course, it is the moon, and it is obscuring our view, and I don't like that, but it is what it is. Can't do anything about that tonight. So there we go, and I'll just do one more little. Yeah. Well, that's pretty good, actually. That's pretty good. So let's go, and I'm going to take it down a notch here. And that's just a little more. Wow, interesting. Here's what I wanted to see. You know, I'm always fascinated with these lunar islands down here because we always see the Maria, you know, the other area of the moon, you know, these gray areas, okay, here, all right, that you see, the dark gray, but we never actually get to see anything but the shadows of the craters. But everywhere you see it's a brighter color, those are highlands, okay, raised areas. The Maria are typically the lowest spot on the moon for that particular area. And again, they're the sites of ancient impacts. That's why they're round, basically. Okay, so when we look at, for instance, when we look at this guy, all right, over here. Oops, sorry. When we look at this guy over here, I'll zoom in a little bit just so you can see. Okay, so we look at this guy. Okay, it's round because that was the site of an ancient impact. Okay, and below it, okay, we see another one that's now the site of an ancient impact. And further, if we look right there where the shadow is, that's another ancient impact, and you can see the rim. The rim is still visible. You know, we're seeing the moon after all these many impactors have hit it, and we're seeing it in the end. We're seeing it basically after it's already been through one heck of an evolution. And so that's the reason that the moon is so varied in its shape and coloration. Okay, right there in the center, there is that gray. You can see that gray ring. All right, that gray, not ring, but the gray area. That's another area of an impact where the lava just overspread the area after the impact. So that's pretty interesting there. And then on other parts of the moon, like this right here, this is actually a good phase to show it. You can see the very complicated ray structure on some of these craters, you see? Very complex, and it's something that is very, it's something that's very, stable. It's not going to change much unless there's more impacts on the moon, and it's going to stay there for all time for us to see. And I really like these rays. I love the way this looks, and I think I told you I recreated lunar soil. That might be one of the streams I'll do after, actually, at some point, is I have to show you my cratering lecture that I do. And I'll do it, live. And I'll show it to you as if you're with me in the room. And we'll actually create craters using my special lunar soil that I made. And you can, if you're interested, let me know if you're interested in that. And what happens is the lunar soil is something that, has clumping properties. It clumps, it has static charge. It does a lot of that. Then So to actually recreate the cratering process is something that takes a little it takes a little effort. So I built the lunar soil to do that, and I think it works very well. So we'll see it. I'll show you. So now I'm getting a question from chat. It says, if those shadows are impact areas, they're not shadows, they're actually the darker color material. If those shadows are impact areas, why do they look smooth and filled in, unlike the one which the rim raised up? Well, that's the nature of the impact. Okay, the impact was such that, okay, let's go over there and take a look. Okay, the question really is, how come we see some that look like craters and some that just look like flat areas like that? In reality, those aren't flat, they're just big. And they have large geometry, very, very big geometry that you can't really see. But when you look at that, if you look at that thing that's in the center now, that Maria that's in the center, that Maria is actually has a border around it of higher elevation terrain, but a lot of it was flooded and filled by lava from the initial impact. So we don't actually see the crater anymore, but it was initially a massive crater that got filled. So it was massive at one point. I mean, that may have been like Saturn's moon Mimas, where literally like 1/6 of the moon is an impact crater. The entire, it's a small moon, of course, but 1/6 of it is an impact crater. It's just massive. So that might have been what we saw here, but lava eventually overfilled this. Then, as more impacts hit the moon, and you've got to understand, when you look at the moon, okay, just look at the craters. I mean, look at how much stuff has hit the moon. You have to understand, even the craters that were formed down here by massive impacts, okay, the material thrown up from those ended up going far up into space and falling down. Like here, look at crater. This is Tycho, right? This big crater down here, right there, that's in the center now. Tycho has rays that go hundreds of miles. Look at that. Okay, they go hundreds of miles, and that's because the impact there was enough to shoot stuff high up into space over the moon, and then it came down. And you can see how it rained down everywhere. Look at it, hundreds of miles. Well, that same effect is occurring, and the stuff falls in these Maria, and you can see some of the craters from the rays from Tycho actually reach. This Maria over here is one that's centering up now. And if it reaches that Maria right there, like I have in the center, well, then it means that it's not just done at once, that many other craters that were formed have overspread their debris, and ejecta, it's called ejecta, the word eject and then ejecta, have spread over and landed in these areas too, filling them in, so that it tends to make the terrain on the moon softer. Not softer as in, oh, it's light and fluffy, but it's not harsh, hard, sharp-edged detail, which is kind of odd because the lunar soil is sharp-edged. It's like glass in some ways. And so when I think it was Harrison Schmitt, when he was walking on the moon, his moon suit was cut through in his ankles all the way to the insulation, and he couldn't do his last moonwalk because of that. Snapple break. Just took a drink. and that's because the lunar soil is very harsh. Now, why would it be harsh? Isn't it just soil? Well, yes and no. There's no atmosphere up there. So whenever a meteorite struck, it would liquefy to molten state that part of the moon, and that stuff would fly up into space. Well, when it would cool, all right, it would cool into a glassy particle and land wherever it landed, and thus become another part of the regolith, it's called, or the soil on the moon. And that regolith has a very sharp and coarse consistency, yet it acts like a fine powder and gets everywhere. It's just a very, very fine, glassy type powder. You can't even imagine what it would be to get that in your eye. Oh man, I mean, you'd have your corneal damage, I'm sure. So the astronauts had to be really careful, and still, in their lunar modules, even after taking off their suits and doing all their best to prevent the lunar soil from getting in the way and causing problems, the lunar soil actually blocked filters on the lunar module, and they actually had to repair them because they were clogged with this lunar regolith, this soil. Okay, because it gets everywhere, and my lunar soil that I made is true to form. It gets everywhere, and when you start using it, you got to wear a mask, and not just a dust mask. You got to wear a full organic respirator. I chose not to emulate the glass particle nature of the soil because that's just crazy, and I've said this before, I think, to you. We don't want people suffering from silicosis, right? Which is the a disease from silica, this type of silica, which is what glass is. So that said, I didn't emulate that, but I think it's pretty cool that it has the most of the qualities. And so, utilizing this in a laboratory setting, I was able to demonstrate how cratering could form, how interesting things on the moon could occur and have occurred. But I think it's also good to understand that when you're doing this, it's really instructional to see just how the moon handles the debris that hits it. And we can't create Tycho's rays, for instance, the same exact way. But you see, it's bright white material. So we put white material underneath the soil, and then on top we put a layer of darker material. Okay? And when we drop a moon mass in that simulates a meteor, it goes down, pumps itself, and it penetrates those lower layers and splashes out, and we actually get rays, just like you see here. And that's actually a good metaphor for how the rays occur. Material that's deeper underground is brought to the surface and spread out, and that's what we're seeing here. What's that tell us? That tells us that when we look at the moon, when we look at the rays and the composition, the chemical composition of the rays are telling us what's inside. Okay? And so those rays give us a clue as to what's actually going on underneath the surface of the moon and what kind of materials underneath the surface. So it's not just about where the impact hits, it's about the rays too. The rays, they do what are called spectral studies of the rays to determine their chemical composition, and they can tell the differences between the rays and the surrounding area. You should look up those studies because they're actually interesting to read. And by the way, just in case I forget to tell you, I think it's a good thing for you to go out to the LROC, the Lunar Reconnaissance Orbiter site, LRO, and look up LRO Quick Map, all one word, Quick Map. And the LRO Quick Map will allow you to zoom in on the moon from all the satellite imagery acquired, mostly from the LRO, but some from the others. And the LRO satellite data will allow you to zoom in to really, literally, to getting 5 meters per pixel. That means for every pixel on the screen, it means 5 meters of the moon is there. So that's like just over 15 feet that you can see. So you can zoom into craters and Copernicus crater and Archimedes and Tsiolkovsky and see all these phenomenal features deep in the crater, right down to little rocks sitting on the mounds here and there on the rims of the craters and in the bottom. You could end up in there for hours. I unfortunately shouldn't admit to you, but I have been in there for hours. Yes, I'm sorry, I've done that. So I think that that's something. Oh yeah, okay. Ken Hancock is not a good question. I think that's something that is, that behooves you to try it. So again, it's LRO Quick Map. All right. Make sure you go there. Go there tonight after the stream. Now, Ken asked me a question. He says, I was listening about the dust, and he wants to know what's my take on the cleaning of the Mars rover. You know, I too have wondered about that, because the Mars rover panels are exposed to the dust and material on Mars. Mars, unlike the Moon, has dust storms. And Mars, like the Earth, can have dust storms that are debilitating and can actually block the entire planet for sometimes months on end. And so these dust storms on Mars are something that will and do cause problems with our rovers. And the accumulation of dust on those solar panels reduces their efficiency, starts cutting down power, and in fact, in one case, we actually had to steer the rover so that it would face the sun more directly at different times of the day, so that it could, get the most sun. Otherwise, it wouldn't have enough to do its job. And you would think that it should be fairly easy just to have a little wiper or something like that. Well, personally, because the Martian environment is it's toxic to humans, because it's all carbon dioxide. There's very little of anything else, and the atmosphere is thin. In order to lift up that faint powdery, it's like talcum powder on the very surface of Mars. In order to lift that, you need winds that are many tens of miles an hour to just lift those little grains. I don't know if you can understand that is how low the air pressure is on Mars. It's so low that the wind speeds have to go over 100 miles an hour to be able to lift that fine talcum powder off the ground, all right, and get it airborne. And that does happen from time to time. And with that in mind, we have to keep in mind that once it gets deposited on the lunar rover, it's not going to bake on, and it's not going to do anything, but you could actually brush it off. And if you were there and just went and just blew on it, it would blow off a lot of it. Okay, some of it will stick, because there is a static charge capability there and ability. But for the most part, we can just blow it off. So you say, well, why don't we just have a dust off, a little canned air that we bring up there? Well, canned air would be expensive to transport all the way to Mars, and so would windshield wipers. Yet, I think windshield wipers, strategically placed, would have been the best bet. Very lightweight carbon fiber material, just sweepers, go whoop, and sweep across. But then people will say, well, if we do a carbon fiber thing, then wouldn't that, besides the additional weight, minimal as it would, couldn't it possibly interfere with and damage the solar cells? And you would say, well, wait, you would just take a brush and wipe it off here on Earth, right? Well, the answer is yes and no. We'd have to be careful, because those solar cells are manufactured a little differently. Now, they're manufactured for space travel, and they're manufactured for the rigors of cold weather and temperature extremes on Mars. But they might not be able to handle the simple rigors of a brush sweeping across them from time to time. So maybe a windshield wiper was considered and not implemented for that reason, because of weight and because of the nature of the damage that the windshield wiper could do to those Martian solar panels. I personally wanted to see windshield wipers, on there to just clean that dust, and the camera lenses. Little tiny wipers on the camera lenses. How hard would that be? Now, we do know, that was a Snapple break, we do know that if we had been on the moon and we wanted to use these little wipers to kind of, clean off the lunar dust, it would only be one swipe and the lenses would be ruined. All right, and you remember why, I think. It's because they are like little tiny pieces of glass. So all you do is do one swipe, and it would just shred it would make the lens all scratched, and it would ruin it. It'd be all cloudy from these microscopic scratches. So there's a time and a place for using this type of stuff. The best is the non-intrusive, where it actually blows it off and blows it off. So how can we possibly do that on Mars? The air pressure on Mars is so low that we would actually have to ship up a compressor on the Martian rover. The compressor would have to run in the background using precious battery power, and the energy budget on these things is really highly controlled. But let's say that we did that. You have to run the pressure up on your compressor so that you get enough air pressure over time so that you can actually go psh, 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 and blow air out in selective places to blow off the panels. That's the best way. But I think that when they determined how much mass it would be to put a compressor on there, because compressors actually have to be fairly substantial, especially when you're in a very, very micro-millibar environment. Okay, micro-millibars, in terms of the pressure. And in that micro-millibar environment, your compressor has to be extremely efficient to be able to take in what little air there is and add and compress and compress and compress. Because it's so micro-millibar, it would have to run for a long time to get enough air to just go and just to give a short burst. And if that's the case, then your energy budget would probably be prohibitive for using a compressor. I'm willing to bet that's exactly why they didn't put one on there. But that's just me. And don't forget, the Viking landers actually had little ovens that actually baked the Martian soil in the effort to look for life. So I thought that was interesting. If they could do ovens, why couldn't they do a little compressor, right? Again, I think it's just the energy budget. I'm just zipping around here on the moon. I'm actually, I don't know why I'm enjoying it so much, but I'm really kind of liking it because it looks so cool, and it's actually really nice looking in spite of the hazy, hot summer night. Yeah. Now that little round crater in the middle, I've said this before, that's Plato. It's 60 miles across, and Plato is a crater that got filled in with lava as well, and it looks like it's sealed. If we zoom in on that, Plato is, that was zoomed as far as I could go, sorry. Or was it? Hold on. Hang on. Let's go. Okay. There we go. Okay, when we look at Plato, hang on. There we go. Yeah. There. We look at Plato. That's 60 miles across, and you can see that it's actually a complete ring. It's not like it's an area that had leakage from, say, down below it, south of it, and in there. This was actually, Plato got filled in because of an impact in Plato, not because of an impact elsewhere that went in there. So Plato was its own, it had its own impact. So pretty cool. Let me just go out. Let me focus. That's about the best I'm going to get it. Well, it's not too bad, I guess. I mean, we could actually, if I just go out for a minute here, I could actually, if I just take it down a notch, I'm going to drop the exposure a little. No, that's not going to really work, is it? Not that good. Okay, just trying to modify, get a little better imagery. Keep the brightness down. So now we zoom in, it's going to see it look a little better. Yeah, there we go. That's pretty good. So does anybody have any questions out there that I can answer for you while we look around the moon? And it doesn't have to be just on the moon. We could actually, we can do it, do anything. Okay, I'm seeing that you got some questions out there. Let me come down here. 1 second. Let me raise up. There we go. I raised up the monitor. I'm reading questions. Hold on 1 second. Well, the lava in the crater that we were talking about, that was from the initial impact, okay? And when it cools, it becomes that darker area that you see. So that's what I was talking about there. So there's no lava there now. There's some evidence that the moon might have a little residual volcanism left, but it's really not thought to have any type of activity right now. That's just the way it goes, you know. We just don't know. So I'm eating some more, and again I apologize because this is a single operation here, a single person operation, and you know, folks are passing me messages in Skype as they can, and I'm trying to get to them. I don't know, Ken Hancock's asking, what do I think about the hue adjusting? I'm not sure about what that means. Oh, duplicate. Yeah, that's a good question. How will the observatory dome, shutter, and then top move around? There's a circuit that I'm getting that will actually follow where the telescope's pointing, and will keep the opening always facing the telescope, so that no matter where it turns, it's going to have that facing out. So it's pretty cool. So I'm pretty impressed with that. I think that'll be a nice feature overall. Yeah. Yeah, Amanda, if you can send questions via Skype, that'd be easier, because I have Skype on my phone, and if I lean over and try and look here at the screen, then I can't really stay by the camera, and I can't see what's going on by the camera. And we're not done. I got other places I'm going to go tonight. We're not going to go just to the moon. I've got other places I want to go. So we'll get there. Just a few more minutes here. I thought I would just let you see the moon while I actually, answer some of the questions you may have, because I think that's kind of a good idea to answer some questions. Like this mosquito in here has a question. He says, "Can I please bite you?" And I'm like, not tonight. How about no? Interesting how part of the moon, the air has what's called air cells. There's turbulent cells that sometimes allow you to see it clearly and then not clearly. And depending on how they actually get to the telescope, you can either see or not see clearly for that moment. And I think that's kind of sad, but it's actually the way it goes. Now let's go out here now, and I'm gonna do something here that it's gonna take me out of the observatory for a minute. I'm gonna run in and get another battery for the camera, okay? Because I have gone through 2 tonight, and I've got 2 more, and I just want to get another one. So hang on, I shall be right back. And if you have any more questions, send them on out. I'll be right back. It really is a pretty night. I'll be back. Okay, I am back. Did we lose the camera yet? Ah, good, we did not. Alright. Oh, that's an interesting question from Derek. He asked about using drones to explore planetary surfaces. So, I think that's an interesting question because there are some plans on the drawing board already to investigate Mars using drones. The thing is, they have winged aircraft that they've designed that fly on Mars. Winged aircraft that can fly on Mars. Now, think about that. The air pressure is like 0.08 of the Earth's. So that gives you an idea of just how much more the wings have to be enlarged to actually be able to function in any way. I think that's pretty interesting, and I don't deny that it sounds to me like a crazy thing, but it's really very possible that you could actually use drones to explore Mars, for instance. And I think that one thing that we would consider is that because we use satellites so much here on the Earth to look at Earth, we'd probably opt for satellites first, and drones only for a more microscopic look at what we're trying to do down there. If you think about it, the Martian rovers are drones. They just don't fly. Now, flying would get us a little farther and a little more, get us to a few more places on Mars. But drones would be interesting. They would allow us to travel farther. But I'll bet it would probably be a good idea. I'm thinking that robotic rovers and so forth would be a really cool thing to use, and I have a feeling that we're going to be doing more of that. Probably, especially when we go to Europa. When we go to Europa, that's going to be a place that we actually have to use drones, because we're going to have to dive under the ice caps and go into the ocean. And we have to do it in a way that doesn't disturb any life that's there. And that's another big thing. Okay. Okay, what do we got here? Okay. Oh, Andy asked what would happen to the Earth if the moon was gone. Well, that's actually very interesting, because if the moon was gone, we would lose the majority of our tides. However, you notice I said majority and not all. The sun is responsible for tides as well. And when the sun is pulling on us and the moon is at a full moon, then the sun is basically and the moon are basically lined up with each other. And so that gives us the deepest tides. They're the biggest tides, right? But we also have the situation where as the moon goes around the Earth, that geometry changes the nature of the tides we get. And so that also is something that helped us develop here on the planet. And now I think that if we looked at what happened if the moon was gone, we wouldn't have any tides that were of substance. So, and I've used this example before in the Bay of Fundy, where the tide is like, 25 feet or more each cycle. That means that the low areas that are exposed by the tides would not occur anymore. Let's say, now what would that mean? Well, if the moon disappeared tomorrow, then the impact on us wouldn't be the same as if it had disappeared 2 billion years ago. If it had disappeared 2 billion years ago, then we would not have had the possibility, perchance, of climbing out of the muck and end up becoming air-breathing mammals. But we have, and that happened for a number of reasons, not the least of which is the fact that we learned how to breathe air because for hours at a time in the tidal flats, we were breathing air as creatures, as lesser creatures than we are. And then the tide would come back in and they would get their water back. So over billions of years, creatures learn to adapt. And that is the secret, remember, to evolution. Evolution is adaptation after mutation. So mutations and adaptations make for a naturally selected success in some cases. All right? So that means this. If you don't breathe air normally and constant exposure to it causes some of your offspring to be born with an ability to, by chance, breathe air a little bit, maybe not a lot, then that creature is naturally selected to succeed and surpass other creatures that can't breathe air, even if only for a little while. So that's how natural selection moves along. And that would happen without the moon. That may not have happened. So, we walk around, and some of you have heard me say this before, we walk around carrying a vestigial ocean on our backs and within our bodies. And that's because of our organ called the skin. It contains a saline solution. That's why your body has salinity and is salty. If you doubt me, just lick your forearm and say, hey, that's salty. You're kind of a human salt lick. And that's why dogs like to lick your skin too. They get the salt. Well, that salt is the holdover from when you were in the ocean. So you leave the water and you brought with you, you bring with you this ocean and you carry it with you around the land. Now it's kind of an interesting thing. Now would that have happened if we didn't have a moon? Well, maybe we wouldn't have left the ocean. Maybe we wouldn't have become intelligent. Intelligence isn't a destination, it's a potential outcome. It's not a foregone conclusion that any species will become intelligent. The dolphins have been evolving for billions of years, millions of years actually, and as they've evolved, their brains are a little bigger than ours, but they don't have high-tech vehicles of any kind because they're just not equipped. Their situation, their environmental stresses didn't dictate that they had to innovate. If it had, then either dolphins would die out or dolphins would have learned how to innovate over time. We can't imagine a dolphin wearing a suit going, hey, I gotta go to the office now. But that said, we also don't know exactly how the evolution of dolphins was so different from other creatures, such that dolphins got the bigger brains, for instance. Because you would think the biggest creatures have the biggest brains, okay, or the most capability to reason, and that's not true. Some animals just never had the environmental stresses in their ecosystems to make a lot of change, and they stayed the same for a long, long time. I've said this before, and I don't know how many remember this, but what's the most successful creature on the earth? The most successful creature, and now what do I mean by that? It's remained unchanged for the longest of any creature on the planet. Which one? Ding, 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 ding. I won't do the Jeopardy thing, but and I don't know if you know that. I mean, I have said it before, and it would be interesting to see. If you remember. But I'll tell you about it. I'll tell you in a few minutes. So, I'm going to read some more questions here. Okay. Ken, you're asking, if Ken's still with us, he's asking, what do I think about the one moon that rotates in the opposite direction? Well, those moons of Mars are probably not native to Mars. It's likely that they are captured asteroids. Don't forget, the asteroid belt is a little out past Mars. It's not like Mars is, it's not like Mars is running through, asteroids all the time. It certainly isn't. But we actually see that Phobos and Deimos on Mars are very irregularly shaped. They're not shaped like our moon at all. They're not round, per se. They have a shape that could very well be a shape that is exactly what an asteroid looks like. And they probably are captured asteroids. And by that, I mean they were captured by Mars gravity many billions of years ago, settled into a reasonable orbit. Mars may have had more. Maybe it captured one first and then the other later. We don't know. But it looks to us like, they are probably captured asteroids. And so whatever the rotation was and whatever which way they were spinning when they got captured, that would probably be propagated to some extent. So that can explain why they're rotating in different directions. So I think it's kind of cool. Anyway, let's see here. What can I do? One more. I want to look at one more thing here. Pardon me as I start hunting here. I have some ideas for what I want to look at, and I'd like to show you. Just a second. Just a minute. Just a minute. Alright, what do we got here? Oh, Ken, that's an interesting question. Ken asks if basically the asteroid belt could have been another planet that got destroyed somehow. It's possible. We don't know for sure. We just know from what we see that when you analyze the orbital locations of the planets, there's a certain predictability to where planets will be. And one of the things that we understand is that some of these possible, sorry, I'm slapping mosquitoes here. Some of these locations, actually, where the asteroid belt is, are a possible location for another planet that was never there, that never did occur. So it's possible that that was a planet. But the question is, what would have broken it apart? And why are there so many asteroids there? It's probably more likely that this asteroid field formed there and just didn't have enough debris and mass to form a planet. And maybe that was because Jupiter was forming. Jupiter has a tremendous gravitational field, and that gravitational field pulls and tugs on everything around it. And so it's possible that the asteroids that were there were not allowed to coalesce into a planet because that we had Jupiter constantly out there, monitoring it like a military commander and just preventing them from actually coalescing with just the right amount of perturbation and gravitational influence. So it's possible, but that we always have to look at the other possibility. So not sure how to answer that, because I don't think really anyone can answer that at the moment. Nobody really knows. I'm going to take us to another object right now, and I'm going to go there now. We're moving. Okay. That's way over. I'm figuring I'm just trying it before. It's actually almost too close. All right, I'm gonna pull back now and pull down the, get us back to high ASA, high sensitivity, so we can see what's going on out there. And let's see where we're at. That's almost, Alright, well, I'm going to take a picture anyway. I'm not sure if it's going to work, but we're going to do 4 seconds at 20,000 ASA. Yeah, I was trying to do something here, trying to catch something. It's there. It's on the right. You can see it's on the right there a little bit, and I will move it over, see if we can actually get it. Then I'm going to tell you what it is. Okay, it's another face-on galaxy to us. And it's actually going to be kind of tough to see because it's actually, my house is in the way. So I'm kind of taking it partially with my house in the way, so it's just going to be just a little difficult. But you can see it in the center there, and I wanted you to see another spiral galaxy before we ended the stream tonight. You can see that this right in the center, that's it. And once we do some live image processing, we'll be able to actually see all these things a little better. And that's all a matter of just getting the images off the camera in a timely manner that doesn't make you wait too long. Alright, so that's pretty cool. That's a spiral galaxy that's out there. It's pretty neat. And I'm going to take us to another one now, which I think you'll like. This one's a little higher. We're not going to have the same problem we had with the others. Had to move my mouse cursor off the screen. I keep thinking it's a star. Okay, 8 seconds at 20,000 ASA. Okay, taking the picture now, so it'll be black except for me in the observatory here. Alright, and there it is. Okay, and that's showing nicely. Okay, this guy right there, you see that? That's actually called the Black Eye Galaxy, and it actually is it's a spiral galaxy, but it has a dark lane, just like that spindle galaxy we saw right at the very beginning. It has a dark lane, but you see how it's sort of curving around the center of that core of that galaxy. So let me go back to it here. So there you see it. Okay. Now, what I'm going to do is to try and get a better shot. I'm going to come down off of ASA 20,000. I come down to let's say 8,000, and increase the exposure to say 15 seconds to see what we get. Okay, so the Black Eye Galaxy is an interesting object because this little guy is really fascinating because it's 1.4 million light years away, right? And it has this shape to it that's really characteristic. That dark lane, you can actually see it a little better there. That dark lane. I have to get the dynamic image processing, darn it all, because I could really do something with this right here for you to show you much better. So I'm going to work that out tonight and tomorrow, and we'll have a way. We'll have a way to do this. I'm going to make sure. Okay, that's my promise. We're going to do this. Anyway, I know how I can do it. I can use the Wi-Fi in the camera, transfer them to OneDrive out on my server, and then I can get at them from the computer here in the observatory. So we might do that for another stream. I'll run through the process and I'll streamline it and get it to work, and then we'll do that. But let me see if I can do another. I got these bugs landing on me all over the place here. Yeah, these darn skeeters, man, they love me. I don't know why. Okay, so the Black Eye Galaxy was pretty cool, and that's, again, it's a spiral galaxy. It's literally 14 million light years away, like I said, and it's got that nice dark lane. And I think it's interesting because it was actually discovered in the 1700s, and it's Messier 64, so Charles Messier at it again. But it's also NGC 4826. Now, NGC stands for New General Catalog, and it's another catalog of objects in the sky. And you know, there's many catalogs. Okay, there's many catalogs out there of objects in the sky, and one of them is NGC. One of them is the Messier catalog, which we're familiar with now from dealing with it. So pretty cool stuff. Let me pop out of this and see what I can do next. First of all, we'll go back and show you that again. So that's the Black Eye Galaxy. Okay. Now let's see here. I'm looking to find a couple of things. Okay, this guy moving. This might be hard because it's actually back looking really close to the house, but I'll try it. Let's do we'll do 15 seconds at 8,000 ASA, and we'll get our instant photo. This is actually called the Pinwheel Galaxy, and if it's in there, then we will have a beautiful pinwheel. But again, the moon is brightening the sky. Yeah, it's there, but it's faint. We'll do so much better once we have the moon gone. Yeah, there you can see that faint thing. And I'm only at 8,000 ASA. I could go up higher, but then it actually makes the scope perform less well because we have that garbage in there, the moonlight. Now, we could go here to this guy. This is M98, Messier 98. And this will be a little higher, out of the way. And let's come back in the exposure. Let's go to 6 seconds at 16,000. And let's just try that. See what we get. Alright. Dun, dun, dun. What do we get? Oh, it's there. It's faint. Yeah, I'm sorry I say, oh, it's there. Like, you don't even, not even giving you a chance to look, huh? Okay, so there you see it right there. That bright area that you see on the whole overall picture, that is Mr. Moon playing the games again with us. The moon is causing this additional brightness. The moon is really bright, I mean, overall, and so it makes it very hard to see some of these objects, unfortunately. And let's see, this is another galaxy. That galaxy there was Let me just make sure I go back to it. M98. I want to get that straight. I want to tell you the background on this, just so you know, because it's only right to do that. Let's see. Okay. Okay. We can't really see it too well right yet, but we will as the moonlight changes. This galaxy is 41 billion light years away. You notice the thing that we're hearing a lot of is these galaxies are many millions of light years away. You know, 10 million, 41 million, 6 million. That's a lot of, there's a lot of light years distance there. Again, the closest one to us is 2 million light years away, and that's the Andromeda Galaxy. And for those of you that were Star Trek fans, that's where the Kelvins were trying to take the Starship Enterprise by reducing their crew to little blocks of waterless cubes, or icosahedrons. Remember that? I know someone out there is going, oh, I remember that. The Kelvins. All right. Anyway, sorry. Let's see. Yeah, I'm getting a. I think my camera's at 8%, but I have more batteries. Not to worry. Okay, so let's pick something else to go see. Oh, you know what I want to do? I'm gonna do another search. I'm gonna do a search. Let me see if I can find this. This thing I'm looking for, if it's available, it's something that would be, yeah, it's not up right now, it's down, so that's not the one I wanted. I wanted the other one. Yeah, I know, you have no idea what I'm looking for, I realize. We talked about that ring nebula before and the planetary nebula, and I want to show you other versions of those nebulae along with the galaxies, along with everything else. So it's just, you know, okay, where is the owl? Oh, good. Well, it'll be bright, but we're going to go to what's called the Owl Nebula. Alright? And the Owl Nebula is actually a planetary nebula, which is a dying star, and we'll see what we got. Okay. Alright, let's take a photo. This will be 6 seconds at 16,000 ASA. And it's there, but you know what? I want you to look at this so you can see. It's hard, okay, but check out in the center. Okay, you actually see that very faint bluish hazy thing. Now compare that to the Ring Nebula that we saw earlier. The Ring Nebula is much brighter, isn't it? Well, this thing here is 1,700 light years away. Okay, 1,700 light years away. And it's very faint, but it's also you know, it's also faint because it's called distended. It's got a bunch of gas that is moved out from the star in the same way we've talked about, sloughed off its outer layers, and there's a couple of things. The distance to this thing is not well known. I mean, they think it's anywhere from what I said, 1,700, to as high as 12,000 light years. So they don't really have a good idea of really how far it is. But if it's really far away, then it means that this gas is really many light years away from that central star that you can't even see yet. Let me just try another possibility here. Let's go to, we're going to do 15 seconds at 6,400. No, I'm not going to do 6,400. I'm going to do 8,000. No, 10,000. Okay. 15 seconds. We're aiming far enough away from the moon where we should be able to get a little bit of this. A little bit. I'm not sure. Well, again, it's what it is. You know, we'd have to do some dynamic processing, but at least we can see the central star now. You can really see it's really faint in the middle there, very faint. But we'll have to come back to this. I think it's good for you to see these objects when they're not when the moon's out, so you can see the effect of the moon. That's actually really kind of important, so you know how much the moon affects us. Okay, and I'm going to now do, I'll do one that we saw before, not tonight, but at another point. Okay, hang on. Here we go. You may recognize this one once we get there. But moving. Of course, you have to see it to recognize it. Okay. I'm going to take a 10-second shot at 20,000. There it is. Okay, let's just go and look at that. Now, this object you can see remarkably well, and it's sort of on the opposite side of the sky as the moon. This that you're looking here, this is the a galaxy that was formerly known as the exploding galaxy. That's because it looked for all the world like it was blowing itself up. But in fact, it's not. It's actually now known as a starburst galaxy, a galaxy that's actually forming lots and lots of stars. You see that reddish area in the middle? Those are those things we talked about earlier, the hydrogen 2 regions, the the H2 regions, areas that are indicative of stellar formation. And it's undergoing a rapid formation process. And we don't know why, but we think that it might have something to do with its interactions with another galaxy which is right nearby, called M81. Again, Messier 81. And this is called Messier 82. They're also known as Bode's nebulae, okay, B-O-D-E, B as in beta, O-D-E, Bode's nebula. And Bode's nebulae are a fascinating pair. So when you look at this particular nebula this way, it's actually a galaxy. Okay, then these galaxies that are like this, that have starburst formation going on, tend to be irregular, and this was thought for the longest time to be an irregular galaxy. But it's actually not. It's actually undergoing starburst formation. So it might be a spiral galaxy, or it might be a galaxy that's had its shape changed by the gravitational interaction with its nearby neighbor M81. And these galaxies are near each other in the sky, but as far as being near us, they're still 12 million light years away from us. And M81 is right nearby. And just for the record, we will go there too, just to see it. So let me just set us up for that. So this is M82, the starburst galaxy, and now we're going to go look at the culprit that actually caused this starbursting effect to happen. And it's right in the general vicinity of this one, so it should be no big deal. And here we go. Okay, heading over there now. Moving. See, we didn't even move much. And you can see in the center of the field, for you with sharp eyes, you can actually see that there is actually a object there. We're going to do 10 seconds at 20,000 ASA. And then you'll see that galaxy that's there that's causing this. Okay, this is the culprit. This guy is gravitationally interacting with M82. This is M81. Alright? And this is a true spiral galaxy, and I've been able to show that and reduce it to see its spiral shape pretty easily. And we will be looking at that in more depth again when I do the live image processing. But M81 and M82 are galaxies that are interacting with each other. This is in the Big Dipper, Ursa Major. Okay, Ursa Major is the constellation, and the Big Dipper is a pattern of stars within the constellation that we know. That's why we call it the Big Dipper. These patterns of stars have a special name. They're called asterisms, like asterisk, but asterism. And an asterism is a pattern, a recognizable pattern that's within another constellation, and that's what the Big Dipper is, an asterism, and the constellation is Ursa Major. So there's a lot of cool things there. Now let's see what else we've got. We got lots of things, but I'm only gonna be getting more and more tired here. Let me do one more before I call it. Okay, maybe not one more. Maybe two more. Let's see. Just a minute. All right, we're gonna do this one. This is called moving. There you go. That little cluster you're seeing right there, that's just to the left of center. This little cluster is a little gem. It's actually, it's called M29, Measure 29, but it's also known as New General Catalog 6913, NGC 6913. And it's an open cluster in a very crowded area of the Milky Way. And even with the moon out, let's see if we can kind of see how much crowding there is there. We're going to do 10 seconds at 20,000 ASA just to see what we got. Because I want you to be able to see just what's going on there. It's not just those stars you're seeing. There's a lot going on there. See that? And that's just that's just the main stars. Okay, there's a lot more stars that are hidden in the star clouds there, and you can kind of see that actually if we look at this. Okay, you can actually see that there's another haze of stars behind there. Now there's some reddening and red stuff in there. Those are artifacts of the camera for the speed that we're using. But this cluster is really impressive because it's actually 5,000 light years away. This little cluster of stars. And you say, well, wait, I lost the cluster. Where is it? Well, we can go back to the live view and you can see it. It's right there. All right. And then when you take the picture rotates. Okay, unfortunately, so it makes it look kind of odd, which is an issue, sadly. So if we, okay, hold on. All right, you actually see it there near the bottom. That's actually what it looks like amid its Milky Way counterparts. But that's pretty bright, you know. And it's Measure 29. It's a neat little cluster of stars. Again, they kind of all form together around each other. And there was a nebula there probably at one point. And as they formed, the hot energy, the stellar winds from these new stars blew away most of the gas and dust that was hanging around. And that's kind of what happens with these kind of clusters. That's why they end up looking like they're kind of isolated out in space. In other regions of the galaxy, clusters like this actually kind of blow a bubble around themselves, and you see a round bubble of cleared gas and dust around them. And that's actually a very interesting thing too. And I think that's just really cool when we see these things. Now, I'm going to go to one that's going to be a little bit faint, but I want to do it anyway because I just want to be able to show you. Again, we'll see it better. And this isn't the cluster, this is actually the remains of a star that has died again. So moving. We're also getting closer to the moon right now, so it's going to be a little difficult, but we're going to do 10 seconds at 20,000 again just to see what we get. Taking the image, and let's see what happens. Wow, well, look at that. If we look at that, okay, you'll see that this object actually has an interesting coloration to it. It's actually kind of bluish green, and it actually has some reddish fringe around the outside. This, remember I talked to you in the beginning about nebulae that are bipolar? We made a bipolar joke and all that, but this is a nebula that is truly a bipolar nebula. Its energy has been blown out the top and bottom of the star, basically the top, North Pole, South Pole, and it has gone, as you can see on the screen, it's to the lower left and to the upper right a little bit, and you can actually see it has sort of an hourglass figure. Well, the narrow waist of the hourglass would be where its equator is, the star's equator was, and those other areas are the areas at the poles where this material sloughed off from the star as it died. Very interesting feature of these, and there's some very small sensitive tendrils in there, which are areas of higher density material that came off of the star, and it's really quite a fascinating object. Now let me see if I can do one better here. I'm going to take I'll go a little longer. I'm going to go 15 seconds. So 2 more seconds at 20,000 ASA. It's going to be too bright, I'm sure, but I just want to try it and see what I get. Also, do you like this other camera that's there showing the telescope and what's happening? If you don't, I can always get rid of it. Okay. There you can see it's a little bit more. There's a little bit more. Little more detail. So this is called the Dumbbell Nebula, and it's, believe it or not, it's called Messier 27. It's 27, which is the 27th object that Charles Messier said is not a comet that he was looking, not a comet. Yeah, Daryl's asking me to check the collimation. You know what? I have actually, and I collimated it, and it's actually perfect. I think that you're seeing what's called on the outside edges. You might see what's called coma, and that's something that is a result of the fast system. It's a fast F system. That is to say, it's only an f6.3. Telescopes like this are usually f10. Now, what does that mean? That means that at 6.3, when you have a 6.3 focal speed, I should say, f ratio, that's a faster optical system than an f10. And it affords us the ability to see things like we just photographed, like we have on the screen. And the moonlight, of course, is making it really, unfortunately, pretty bright. But we would get the ability to take pictures of these things that are much clearer and brighter because the optical system is faster. You know, it can acquire light faster because of the way the mirror is made. Typically, scopes like this are f10, and we don't want we don't want to have an f10 telescope when we want to be able to see objects like we've been looking at, like galaxies and things. We would not be able to do the kind of things that I want to do with an f10 telescope. So this is the Dumbbell Nebula. Again, it's M27, Messier 27. And let's go. I might be able to. I'm looking for something. Hang on, I'll figure it out. I want to see if I can go there. See if it's able. Okay, moving. All night tonight we've been looking at a variety of objects, and we've been looking at open clusters a lot. And here's another open cluster that you see right there on the screen. This open cluster is called Messier 39, and it's in Cygnus, the Swan. We'll take a photograph of it so you can see at 20 seconds at 15 seconds at ASA 20,000. And you'll see a little better what it looks like. Here we go. It's coming in now. Okay. Now, that's really pretty because it kind of shows you, this is in this middle of the Cygnus Milky Way. You can see, and again with the, unfortunately with the bright moonlight, Now, over on the left side, I think that's really interesting, because when you look over on the left side of the image, you see there's an orange star right next to a blue star, and then you've got a number of stars all around those. Now, here's what's interesting about that, and I don't know about this particular location, but usually when we see that, it means that those stars are kind of in line, in our line of sight, and that they're not really near each other in the sky, perhaps, but these could be. And I just think that's a very pretty area over there. So, this is a star cluster in Cygnus called M39. It is an area where, this is what it looks like to your eye. Alright, but when you take a picture with the camera, you saw what it looks like. It's actually got a lot going for it, a lot of interesting, a lot of very interesting stuff going on there. And I'm going to move. Again, every time we see these open clusters, okay, I want to point out here, we saw, remember the wild duck M11, which was very, very tight. It looked like a globular cluster, but it wasn't. And then we saw some other clusters, open clusters, that had some nebulous clouds with them, like the Lagoon, M8, which are star-forming regions. Now we're looking at M39, which is sort of sparse. There's only a few stars. And the stars we see here are pretty much the stars that are part of that. Now, keep in mind that you're looking at it in 2D. You're only seeing what looks like flat. But those are in 3D, so they're actually, they have some three-dimensionality to them, meaning that some of those stars are closer, some of those stars are farther away, that kind of thing. Now, another question that just came in was, what's the temperature between the stars? And rather than go off into chemistry and all that stuff, I'll just say, temperature is related to pressure. So in the vacuum of space, there is no temperature. It's undefined, and it doesn't satisfy the human need to say, well, no, I want to know what the temperature is. If I could touch a piece of space, would it be hot or would it be cold? The answer is it would be neither. And the reason has to do with the following interesting bit of information. In space, you only have absorption of radiation and reflection of radiation, okay? And that translates to an object's ability to take in radiation or to have a high enough reflectivity so that it doesn't absorb so much. Okay, a piece of ice in space, for instance. A piece of ice in space, typically people say, oh, well, in the sunlight it's 400 degrees and in the shade it's minus 400 degrees. Well, actually, that's sort of a misleading statement. It's not true that it's 400 degrees in the sun, because in space, in the vacuum, there is no conductivity of heat except through materials. So that means that if you're a piece of ice, the radiation hitting you can either be absorbed or reflected. If the radiation is absorbed, it gets converted into heat and reflected back out, or sent out through the structure of the ice. So ice that goes away over time in space is called sublimates, and when it sublimates, this is the process by which a piece of ice will go away in space or disappear. It absorbs enough radiation so that over time it'll basically vaporize little by little and then go away. All right. So that's all we talk about in space. It's just absorption, or it's non-absorption of radiation. All right, and that has a lot to do with an object's albedo. So in between stars, for instance, there may be dust grains. There are very small micron-sized particles through space that are dust, interstellar dust, that can absorb radiation. And what it does is it'll heat up internally and radiates it as infrared radiation or heat. So when IRAS, the infrared satellite that has mapped the galaxy in infrared, IRAS can see these dusty areas and what they look like because it's mapping the infrared energy and emissions coming from them. So in between the stars, basically, it's undefined. In chemistry, if you want to go there, I mean, we have the ideal gas law, you know, PV equals like nRT or something, and that means that, and I think it's temperature might be T to the fourth, I'm not sure, I have to look that up. Oh look, I have an exhausted battery. Okay, that's easy, because I have a non-exhausted battery to go right in. So, and now we put that right in. Don't worry, I'm going to get an electrical backup and have a battery that can just do what it has to do. Okay. Okay, good. So, I hope you understand that. I hope that was sensible. If you have any other questions about that, let me know. You can also leave them in comments on the videos. I'll be happy to get back to you there. So for any of you that didn't get an answer to your questions in chat, please don't think that's the end of it. Okay, I don't want you to be left out in the cold, so to speak. So please do leave a message on the video once it's up, and I'll be happy to go back and answer those. Alright, I don't want you to think that I'm ducking any questions whatsoever. Alright, let's go one more place here. I'm going to take off to this little spot. Okay, we're going up to Lyra again. See, it looked like it was going to get away, but it's not. Okay. Okay, that's a very interesting object there. We've talked about this one before. That is actually what's called Epsilon Lyra, and Epsilon Lyra is actually a double star, but it's also, and this is the thing that I want to show you if I can. Oops, other way. Okay. Now, this is a double star, but it's also a it's also a double-double. If you notice, the stars don't really look perfectly round all the time, and that's because they're not. I'm going to come out of here and I'm going to drop the exposure and take down the ASA a little bit, and I don't know if we can do it, but I want to try and use the scope to show the separation of these stars. So I'm just going to do a little experiment here. Let's see if this works. I'm going to do 3200. Well, actually, I'm going to drop it all the way down because these are stars. I can do this. Okay, let's get down to, say, 400 speed film. Okay, and we're going to do it at a 25th of a second. Let's try that. Doesn't look like much, I know. But let's zoom in now and see if it helps us see what we want to see. Now, we're trying to discover the true nature of these, so we want to check them out. Okay. Interesting. You can kind of get a little bit of it. And what I'm saying is, these two stars, the main stars, are going around each other. And then each of those stars is itself a double. So this is a double-double. The one at the bottom is a double star, the one at the top is a double star. And they're orbiting each other. So now let me just drop it down a little more. I'm going to try and get it just barely on the fringe of viewability, because I actually want to see if we can actually, I want to see if we can get the double status. Well, I would have to probably do what's called eyepiece projection, but I can see that those are doubles, but you can't see them as two separate double stars like this. I'd have to actually be zooming in closer than my camera will do. Keep in mind, what the camera's doing is miraculous, actually. But the double is interesting because we don't know of any planets around these guys at all, but it is fascinating because these particular stars do have an orbit about each other, and then they have their components. Each of the double star elements are going about each other as well and orbiting each other. So I think it's just a really cool double star system. Well, double star, you know. Now, these stars are 162 light years from us. Okay, so that means that you can actually figure out, you know, being that they're that far from Earth, you can figure out how far they are from each other, and you can figure out what the actual distance is between them. The stars themselves, the doubles, okay. Yeah, the doubles are basically 160 astronomical units apart, which is interesting. Okay. Now, the time it takes for the time it takes for these stars to go around each other is 1,200 years. That's the length of time that these things are in their orbit, orbiting each other. I think that's actually a pretty amazing orbit. Now, as far as let me see now. As far as these small components, each component, each of those components takes probably about 600 years to go around each other. So they look like they're really close together, but they're really not, because don't forget, they're 162 light years away. So technically we don't know this, but it's possible. It's possible that we're seeing these things, you know, as well, we know that we're seeing them as they were 162 years ago. But it's interesting that when we look at them, we don't have any idea what they may look like now. We can only guess. You know, so, and Ken, you're asking me a question. Isn't the speed of light slowing down, though? In the context of what part of my conversation, Ken? You can just throw that in, so I know. Okay, so now Amanda, you're asking, you heard about vampire and zombie stars. Well, vampire stars are interesting because what they do is they actually basically feed off of other stars, and usually you might have a white dwarf in a binary star system where you have another star that it's actually circling. The binary star, the dwarf is circling, say, another star, and in that binary system, the white dwarf is sucking off the outer envelope of the other star. Now, that causes a number of things to happen because it makes the white dwarf receive all this new material on its surface, and the white dwarf is really already this material that is very, very compact, and it doesn't take long for it to basically become too much, and then the white dwarf basically in a sense, erupts it off, and that's actually called a nova, not a supernova. It's a nova. And every now and then, these stars, some stars will actually get really, really bright, and what it is, it's actually the white dwarf companion in the binary system that's suddenly spewing off this stuff. So it's pretty cool, and I think it's that's kind of what a vampire star is. And then you're asking what's going on between these stars that we're seeing here. Well, not much. I mean, they're not. These two stars here aren't really doing anything but orbit each other. Now the two components, okay, they're like 162 or 160 astronomical units apart. Not these two that you're seeing, but the components, the two we can't see. Those are actually about 160 astronomical units apart. And then the two stars are also much farther apart. Those two stars are several light years apart, actually, that we're seeing on the screen. So, as far as what's going on with this, the double components, the doubles of each of the end stars, again, not much. They're not close enough to really be physically interacting, but it looks like they are. Now the question is, will we be able to see those at some point? You bet your butt. I'm going to make sure that we can get a nice system to zoom in on these a little bit more, and we will have that at some point. All right, I promise you. So let's see. Well, Ramiro, that's a good question. If the Earth was going to explode and I had a spaceship that could take us up to 100 light years, which star would you pick as the most likely place for a planet to support life? Well, we would actually have to consider all the exoplanets that we found. Now, there's been a couple of planets found fairly close to the Earth that might be candidates. But you see, to date, we don't really know, Ramiro. We don't really know whether they have atmospheres. We just suspect maybe they do. We don't know if they do. So, that would be a shot in the dark, to be honest. And I might, who knows? I might choose. I would actually like. I don't know. I might choose the TRAPPIST-1 system. Just for fun. I mean, TRAPPIST-1, is an interesting system in itself. What's that? No, Amanda's asking about. Sirius has a component. Okay, but we haven't found any planets around Sirius yet. Not yet. And when I say component, Sirius has a white dwarf companion, which means that it's gone through a real troubled past already. So it had a star that was, much bigger, and now it's, gone down to a white dwarf. We're seeing it at the end of this particular stage. So, okay, let's see here. Alright, well, let's see. I'm gonna move ahead here, which actually not there. I'm just looking around. Don't worry about me. Don't worry about me. I'm just looking around. I'm just looking around. Just looking around. Don't worry about me. Okay, 1 second here. Okay, now we're going to go to another double. Right. This is another double star. And I'm going here because it looks like it has about the same separation visually, okay, as the others, Epsilon, Lyra, the other two we just saw. But the difference is they're stars of two different brightness. They're not double doubles, okay, and it's actually 414 light years from our planet. The other one was 162 light years. This is 414, and these are still double stars. Now, what's interesting is this brighter one here is actually what's called a giant, and it has a surface temperature of only about 3,500 degrees, but it's a little cooler than the sun. But it's actually 67 times the size of our sun. That's the one in the upper side there, in the upper above. That star, okay, let me just zoom in a little here. That star is, you know, really, really massively large, okay? And you can see another component right there. That's the component of it. It's 637 times the brightness, the intrinsic luminosity, it's called, or the intrinsic brightness of our sun. 637 times that of the sun, and it's like 1.2 times as massive. Now, that doesn't sound like a lot, but when you consider that it's a giant star that's 67 times the diameter of the sun, well, you can actually do that math if you want. And the diameter of the sun is, 864,000 miles, say 1 million miles. So this star is roughly 67 times that, or 67 million miles. Well, an astronomical unit is 93 million miles. So this thing would certainly be encroaching on and passing, I think, the orbits of Mercury. And so it'd be a big star. And this is a double star, and you can actually see it really cool there. And let me just get a little bit. Okay. So just for the record, so I can show you here. Okay. That star down below is not what I'm talking about. Okay, the star we're looking at is called 42 Hercules. It's a star for 42 Hercules is actually the designation of the star, and that little star to the left of it is the actual component of the binary star. Now, what's interesting is this is 400 light years away. And that star over there, that one on the left, that little tiny component, that distance corresponds to 3,500 plus astronomical units from the star. Alright? So that's 3,500 times 93 million miles distance away from the star. It's a massive distance. But they're still binaries, they're gravitationally bound. Right, so let's just, for fun, let's actually take a picture. We'll do 6 seconds, and I'll do it at 10,000 ASA. Let's see what we get. Oh yeah, look at that. It's pretty. You know, I like looking at these. These are like little jewels. You know. And again, that bright one is a giant star. Alright, it's classified as a giant. 67 times the size of our sun, and it would go out way, way past the sun's diameter. So you can figure it out. It's beautiful. Alright, so now I'm going to end the stream shortly, and I'm going to end it by going back and bringing up one more time. I want to bring up our moon. We're going to go visit the moon again one last time for the night. I don't know if Paul and Keith are streaming tonight. Maybe they are. But I would actually like to, I'd like to go back to the moon for one more view before we go to bed. You know, all of us, we're all going to go to bed and go to sleep. And I'm trying to see if there's any holdout for anything else we can see here. So, and there really isn't. Okay. All right. Off to the moon. Moving. Oh, that's like nuclear moon. Sorry about the noise of my stool there. Ah, yes. Nuclear moon. And now we just drop down this. Alright. And let's go see. What if we go? And I'll come in. And over there. Let's just go around here and see what we got. Wow, that's pretty cool. Looks nice. Looks nice. Cool. Well, this is great because you can go from this stream, you can run over and watch Dave Schock on Coast to Coast. I think those guys are doing a great job. I can't wait to see results from CubeSat. And I'm a big supporter of CubeSat. Dave. They support our UFOTOG 2 project. Beautiful. I'm trying to read your comment here, Keith. What's that mean? Fake CG, huh? How'd you guess? Interesting. I like when the moon gets to this point, guys, where it actually ends up, you know, showing a little shadow, because that's really cool. Because then you get to see, you know, some contrasting areas you don't get to see normally. I like that very much. But it's a hazy day, hazy night. The moon's got a little bit of problems, a few little issues. Okay. Don't worry, I'll have music. So if I was going to do this with music, I could do that. But not yet. Somebody's getting me some music. And that somebody is in the chat. Alright. Anyway, I hope you guys enjoyed the journey tonight. And we will end on the moon. And I will talk to you, I'm sure, at another point. I am glad you guys joined me tonight, and I hope that you actually had a good time. But let me know and give me an indication of what you thought, and I shall return. Alright? So I will end the chat and I'll talk to you again. Thanks, guys. I know it's a little bit awkward the way I end the chats, but hey, or in the streams, but I'm the only guy in here. I'm doing everything. So anyway, leave me any questions and I shall talk to you soon.